然后你点个张三，我圈，你要让别人。
Audio, okay. So,
Okay, how's that? Okay. Everybody make sure sound's off on your computer. How about now? Okay. It's still coming out on somebody's computer. I don't think it's mine.
yes, it's for me, right?
Yeah, my audio's off.
Yes.
How about now?
Okay.
Okay. Hey, I hear no reverb. Okay, that's good. Good morning. My name is Chris Cox. I'm a professor in the math department and department head. And so I was asked to give a first couple of presentations this morning to start off this quantum computing workshop. Okay, this is a very exciting time to be at UTC and be involved with it. Talk a little louder. Ed, sure. Keep asking if I'm not talking loud enough. So that I work on projecting my voice. So Reinhold Mann is going to come by, I think, between the first two presentations, right? You and say a few words because he's busy right now. He was going to give the lead off. So I'm just going to launch right into the first presentation. I'll say right up front that I'm much more the learner than the teacher here, okay? Quantum science is a fascinating field, but I've really only been involved in the effort here seriously for a year or so, okay? And but I think that's really exciting in a class to know that the professor is sort of learning along with you, or maybe just trying to keep ahead of you, rather than teaching it for the 10th time. So I think that's a good thing too. I'm real curious about the audience and who's here and what your background is. So how many of you have had a calculus class? Okay, how many of you have had a linear algebra class? Raise your hand. How many have had a functional analysis class? Not quite so many. Okay, the mathematicians, at least most of those. Anybody has a upper level or graduate degree in math has probably seen functional analysis. Quantum science is a fascinating field for us, partly because it has so much math in it. You just can't escape the math. I've got some quotes that'll illustrate that from a lot more learned people than I am. I don't think I need to convince you of that. Putting together these slides and thinking about it as I was walking down here, in a sense, this is really 3 or 4 short courses. I mean, we could give a day's lecture on any one of about 3 different topics in here. Whether it's the linear algebra, whether it's the functional analysis, there's just so much here. And so my goal is at least to point you in directions, okay? I'll throw a lot of terms and things at you. Those that have seen them before, some of you are going to get bored. I'm sorry for that. For those who haven't seen it for a while and it's new, I hope it piques your interest. I would love it if it convinced you to go take another math class. Okay, that'd be great. So I'm doing this in 2 sessions. I tweaked the topics just a little bit from what Dr. Liang put together to make it, maybe, I'll be honest, a little bit easier for me to put together just because of the time crunch I'm under. He had listed a little bit about, he called the second session originally something about programming. I'd really prefer to leave that to the expert. There's plenty of math to talk about in the first 2 sessions. So I just called these Math Foundations 1 and Math Foundations 2. Okay, that's what this is going to be. So here's an outline for the first session. I'm going to give some quotes and some comments to motivate the topic and go over some notation and definitions. That's a large part of any upper level math class, really. It's just getting through the notation, right? Getting familiar with that hint. And introducing quantum science is a whole other set of notation that the physicists use, okay? And I'm going to do what some of the textbooks, for example, I will refer to Hadari's book. And what I like about his book, he has a lot of math in it. And he first expresses the math in the standard math notation, then he eases into the physics notation, all right? That's kind of what I'm going to do. And when Dr. Liang and Dr. Lee talk later, they'll have more of the, especially Dr. Lee, will have more of the physics notation, the Dirac notation and things. I'll have some of that, okay? I'll start exposing you to that as well. So linear algebra is really the heart of quantum science in terms of how it's characterized and expressed. So we'll talk quite a bit about that. I was asked to talk a little bit about complex numbers, which I will, but I'll also include a reference because there's plenty of references out there where you can look up the terms. I'll talk very briefly about tensors. They play a role here. Tensors play a strong role, especially they're important in higher dimensions. And then I was asked also to give an overview of probability. Okay, so gosh, there's 2 or 3 classes right there. Okay, but we'll talk about that. I would guess that by the time I'm getting to probability, I'm going to cut some things off and let that spill into the second session. But let's see how this goes and how our time goes today. So, the question.
Will you spare us the proofs?
Oh yeah, the proofs. I promise. I promise no proofs. Well, there is one sort of proof towards the end. Yeah. Great question. All right, and this is informal, okay? You're welcome to, especially if you can't hear me or I'm talking too fast. I lived in South Carolina for 34 years, so I lost a good part of my native Ohio accent. I started talking a little slower, but if you can't understand me, just please ask or ask questions if you can't hear what I say. All right, so 2 of the best known quotes about quantum physics are the first, right? From Richard Feynman, who said, I think I can safely say that nobody understands quantum mechanics. I like that. And Niels Bohr said, if you're not confused by quantum physics, you haven't really understood it. There's kind of an oxymoron in there, but I like it. Okay, all right, confused and understood. How can you really understand it if you're confused? But anyway, that's a great quote. A very well-known book that I first heard about from folks at Oak Ridge is the book by Nielsen and Chuang, and the scientists at Oak Ridge said, if you want to look up Mike and Ike, okay, because their names are Michael Nielsen and Isaac Chuang, and to give credit where credit's due, if you want to, I really should give them better credit. The book is called Quantum Computation and Quantum Information. So, because the best known, I think, right now is the 10th anniversary edition. Okay, but if you type quantum and Mike and Ike, that book will come up. Okay, you'll see it. I highly recommend it. And again, the title is Computation Information, but they talk a lot about just quantum mechanics itself, because they're physicists, right? I know Nielsen is. But they say there the postulates of quantum mechanics were derived after a long process of trial and mostly error. I love that phrase. Okay, I really appreciate that. And which involves a considerable amount of guessing and fumbling by the originators of the theory. How many professors have told you that at the beginning of their class? Not very many, but that's true. That's how research is done, okay, for the most part. There's a lot of mistakes made. So I really appreciate them saying that. Another good book is by Griffiths and Schroeder. And they say quantum mechanics is not something that flows smoothly and naturally from earlier theories. That's kind of a scary thought. On the contrary, it represents an abrupt and revolutionary departure from classical ideas, calling forth a wholly new and radically counterintuitive way of thinking about the world. And that's why it makes it so fascinating. Okay, but this is a subject that makes me wish I was 20 or 30 years younger. I wish I would have gotten into this a while back. It's just a fascinating field, and it's very exciting. It's a very exciting time to be here. So the book that I picked to use for a course that I am going to teach this fall. I should say probably. The problem is about the book. I'm teaching one of the 4 courses in the undergraduate certificate series that Dr. Mann and Dr. Lee and I set up. And that course is the math foundations of quantum information science and technology. Andrew Lukarsky is a bright younger physicist out on the West Coast. And he's taught like at Reed College and other places an undergraduate version. So I thought his book would be reasonable to use. And he has a couple of quotes that I like in there. He says, quantum mechanics is a theory in which linear operators and vector spaces and eigenvalues are central. Okay, so that's why linear algebra is important. It emphasizes that. Fundamentally, quantum mechanics says that the universe is described by linear operators on a complex valued vector space. Any of us, when we first took complex variables, we wondered what in the world to use this stuff, right? Right, but there it is, right there. And another quote from Nielsen and Chuang is that, in our opinion, the chief obstacle to assimilation of the postulates of quantum mechanics is not the postulates themselves, rather the large body of linear algebraic notions required to understand them. Okay, so I hope I'm convincing you that linear algebra is important here. Okay? It is. It's a fundamental aspect of what you need. I'll bring in early the notation that you see when you start studying quantum mechanics that the physicists use, specifically Paul Dirac. From Hidari's book, and I got a lot of these great sources I got from Dr. Reed. He gave me this one. He will hear talk this afternoon. Hidari says it's important to note the difference between the zero ket, that's called the zero ket, and the zero vector of traditional linear algebra notation. So if you haven't seen this thing called a block sphere before, okay, that's something you'll see a lot when you study quantum mechanics and quantum science. But it's not, I have another slide that just shows it's not like, it's different from the 3D that we learn. It's different from the 3D that we learn in Calc 3, okay? So we have to keep that in mind. The zero vector represents the origin point in a vector space, and it has nothing to do with the Dirac zero ket. Okay, keep that in mind. In Dirac notation, we denote a column vector as a ket. That's the symbol on the lower left there. It's called a ket. And the conjugate transpose of the column vector as a prop. That'll be the conjugate transpose of that. We'll talk about more of that notation later on. And the column vectors and represented succinctly in that form at the bottom. So just keep that notation in mind. So notice, for example, where the 0 and the 1 kets are labeled at the top and the bottom. They're opposite each other on that block sphere. All right, so a few more remarks. So the quotes on that previous slide remind us to be mindful of definitions and accompanying notation. Okay? And some conventions are discipline dependent between, for example, math and physics. The physicists use the block sphere, and when they on the block sphere, look how they label phi and theta. Okay, phi is the angle in the xy plane, theta is the angle from the vertical. When we learn Calc 3 in a math course, we label theta in the xy plane and phi. I have two different forms of phi there, but they're both phi. Phi is the angle from the positive z-axis, right? So just keep that in mind. And if you're not sure, just ask about it. So we'll use the physics for it. Right? We're sticking with that. And now we'll go on with a brief discussion of more notation. We'll review some of the relevant topics from a sophomore level linear algebra class. And we'll talk about real arithmetic first before we go to the complex. And see, I'm kind of being mindful of my time. So I was going to go from 9:15 to 10:30. Now I'm going from 9 to 10:15, right? Right. Okay. All right. So notations and definitions. So some people like to use parentheses on their vectors. Some like to use square brackets. I like square brackets. They're the same thing. Okay? Often for vectors, you'll use bold font. It's hard to draw when you're just writing. Or engineers like to put arrows over things. Again, take it in context. Mathematicians tend to be lazy. I like to say constructively lazy. But again, we take it all in context. If we have a vector like a vector of two elements, x equals AB, with this transpose. You turn the 2 by 1 into a 1 by 2, right? One in. And a matrix transpose for say A has 2 rows and 3 columns, right? What's the size of the transpose? 3 by 2, right? And what do? We reflect everything over the diagonal. The first column becomes the first row. In this case, we reflect everything basically over this diagonal here, right? In other words, the first row of A becomes the first column of A transpose. The second row of A becomes the second column. You've seen the transpose before, right? One of the simple matrix operators. Okay, just keep that in mind. Yeah, an M by N matrix will have a transpose that's an N by M. Okay. I need to start simpler today. I'm only on my second cup of coffee. Okay, complex conjugate of a number. Okay, I is the imaginary unit, A and B are real numbers. So the complex conjugate is sometimes denoted with an asterisk, x star, x asterisk. We just turn the imaginary part, we change the sign, A minus BI. The conjugate transpose of a vector. There's a lot of different notation for that. If A and B are, in this case, are complex numbers potentially, I haven't really seen the DAG notation before until I started looking at quantum science. But this is like the dagger, that dagger notation. Sometimes you'll see conjugate transpose, X bar transpose. But again, being constructively lazy, sometimes you just use asterisk, X star. But again, taking the context. If X is defined as that vector, then X star is the conjugate transpose. That's all it is. And there's a nice discussion on Reddit about what's your favorite way to write that. Okay. So I use resources today in making this talk over the last couple of days that I wouldn't have used 10 years ago, right? I use the internet a lot. I use this interesting app called Matrices that Dr. Malfers told me about, because I took some slides that were PowerPoint and in very limited time, I turned it into LaTeX. All right, Matrix is a really cool app, MATHPAX, because you can do a screenshot and it generates Word or LaTeX or other forms of things. The other thing I used that I wouldn't have used 5 years ago was I used ChatGPT a little bit. Our students use that a lot more than us. Okay, so I use that carefully, but I used ChatGPT the other day to determine whether some springs on the internet were compatible with my dishwasher or not. Okay, I wouldn't have done that 2 years ago. Which is really interesting. Our dishwasher door flops. I put springs in it. Okay, so anyways, again, the key point is probably take things in context. That's what we need to do. I'll say that again. The adjoint is another name sometimes used for the complex conjugate. That's also used in an abstract sense when you talk about operators, which we'll talk about later on a bit. Okay, talk about operators. And sometimes people use A superscript H, meaning the Hermitian transpose. All right, so I usually stick with star. It just makes life simpler. Let's talk briefly about vector matrix operations. Just some simple things again, just to warm up, get our minds working a little bit. If we want to multiply two matrices, suppose we want to form C equals A times B. C equals A times B. And the question is, A has M rows and N columns, and B has P rows and Q columns. Let's suppose they're both just real matrices. What has to be true in order to form the product? Two of those parameters or sizes have to be the same, right? The inner ones, N and P have to be the same, don't they? Okay. And how is it carried out? Okay. Well, we can talk about vectors and rows that element ij of C, it's a product of a row times a column, right? It's a product of the ith row of A times the jth column of B. Or if you just want to write it all in summation notation, we can write Cij equals, say, the sum over K of what? A ith row, kth element, B kth element of the jth row. Does that look right? That's what we learned in linear algebra class, right? The next question is, what size is the result? What size is the result? So I like to do things like where, when I write this out, it's been a while since I taught this, but I write M by N here, I write P by Q there. I remind myself that these have to be the same. Where do I get the size of the result? From the outer indices, right? Yeah, the result is just a M by Q matrix. Is that right? Does that make sense? Do we do anything different if A and B are complex? In this case, I'm just talking about matrix multiplication. The answer is no. Everything's carried out the same way. Okay. There is a case where we have to worry about taking the conjugate of one of the things, but we'll get to that. That's not true here. You know, the same process. And when I give a brief review of complex numbers, I'll talk about multiplying complex numbers. But that'll be just a reminder. Everything okay so far? Is my voice projecting okay? Okay, thanks. Okay, let's do a quick example of matrix multiplication, just again, to make sure my juices are flowing okay. Suppose I take a 3x2 matrix A. And this is one, I'm not going to fly without a net on this one. Just, Oh, I think I could. It's not that hard. Suppose I take A having 3 rows and 2 columns and B having 2 rows and 4 columns. So the first question is, did I give you one that works, right? Let's how do we check that? So A is 3 by 2. B is 2 by 4. That checks out, doesn't it? C, the result is going to be 3 by 4. The first the 1 element is going to be the first row times the first column. That's going to be -3. In fact, by the nature of this term here, the first column of the result is just going to be the negative of the first column of A, right? Okay. I'll redo the last column and see if you see if you fill in the rest. We'll check with you later if you can. I think you get this. Have you seen this? Well, I see a PhD student check. I had math. Make sure. Okay, you're familiar with this, right? Just okay. All right. The last column is going to be what? This element is going to be 3 times 3 plus 4 times 1. Right? The very bottom column is the last row times the last column, 0 times 3 plus -1 times 1. Right? Okay. All right. You got it. You got it? Is that okay? All right. Okay. So let's talk about the typical topics in a linear algebra class. We've already seen a few of those. We would talk about systems of linear equations and their solution. Most common way to solve a linear system is by Gauss elimination. You might learn Kramer's rule, determinants, right? Right. The fact is, it's unstable for especially computationally as matrices get large. But it has interesting algebraic properties. Determinants, if you know about determinants, we'll talk about that when we talk about eigenvalues. Vector spaces, we'll talk more about that. You see the subject of linear dependence there. These are all things that we're going to talk about here. Subspaces, inner product spaces, linear transformations, and eigenvalues and eigenvectors. Okay. It's really interesting from that earlier quote that quantum mechanics involves complex, but things that are linear. You know, the most famous PDE in quantum mechanics Schrodinger equation, which is linear, right, Jamie? And so Jamie is studying nonlinear aspects of that. Right, the fundamental theorem of linear algebra, which we'll refer back to at least one of the results from this later on. So for an n by n real matrix, and there's a generalization to complex, the following statements are equivalent. Equivalent means that if one of these statements holds, then they all hold. If one of the statements 1 through 5 does not hold, then they all fail. Okay, we won't prove this, but if you did prove it, the proof would be to start with 1 and show every other statement follows in a chain. That's how you prove it. The linear system AX equal B has a unique solution given any B. If that's true, then it follows also that the only solution when B is 0 is X equals 0. And also A has an inverse that you can multiply by A and get an identity matrix back. The identity is what? 1 over diagonals and 0 everywhere else. The determinant of the matrix is not 0. Okay. And finally, this thing called the rank is equal to n. And the rank is defined as the number of linearly independent rows or columns of A. What does linear dependence and independence of vectors mean? They are linearly independent if the only set of coefficients that you use to form a linear combination of them to set equals 0 is when those coefficients are 0, right? You cannot form any one of those vectors as a linear combination of the other vectors. That means they're linearly independent. And keep that in mind. And there's some related results. The rank of the matrix is also the rank of its transpose. The range is all of the right-hand sides that you can hit think of A as shooting X into something and getting a result. Right? The range is all results you can get by multiplying A by a matrix X. And the rank is the dimension of that range. Okay, but we'll talk more about dimension later on as well, what that really means. So let's talk about vector spaces and norms. Norm on a vector space is a function usually denoted with those double absolute value signs that satisfies these three properties. And there's variations on this, but these are the key three properties that a norm satisfies. For any elements u and v in that set, in that vector space, and for any scalar multiple alpha, the norm is always non-negative. It's always bigger or equal to 0, and it's 0 only if that thing u is equal to 0, only if that vector u is 0. If I take the vector multiplied by a scalar and take its norm, it's the same as taking the norm of u and multiplying by the absolute value. And finally, there's something called the triangle inequality, which is called that because you can equate what we see there, the sides of the triangle, and talk about it that way, that the norm of the sum is less or equal to the sum of the norms. Okay. So that's called triangle inequality. The reason these are useful is because they give us a scalar quantity as a measure of things that have multiple entries in them, like an array or a vector or a matrix. They give us a way to compare things. Okay, and talk about sizes of those things. They're very useful if you're doing numerical methods and talking about errors. Okay, errors in your numerical solution and ways of talking about those. The most common example of a vector is an element of the real numbers within prime entries. But vectors can be a variety of things. They can be very abstract. But for our purposes, we'll mostly be talking about real or complex n vectors as well. Okay, but we can talk about matrices, we can talk about polynomials. You can go off, all kinds of directions with vector spaces. But for us, there'll be n vectors with real or complex entries. Okay, so let's talk about some specific norms. The ones we normally would cover in an undergraduate numerical methods class in your algebra would be what are called P norms. One of those you're very familiar with. You're familiar with the 2 norm, which is just the Euclidean norm, but it generalizes to the 1 norm. You make P equals 1, and all you do is add up the absolute values. Question?
Your example of vector space, there would a Hilbert space be a vector space?
Under some other conditions. Okay, which I'm gonna give you all of them. Okay, good question. All right, I didn't ask him to do that. That's good, great question. Yeah, that's in the session too. Good, great question. Yeah, great question. Anything else? All right, yeah, I'll draw a Venn diagram and show how those things fit. Infinity norm, that's the simplest one. That's where you just take you compare all the absolute values and entries and take the largest one. Okay, let's do a couple, just one more example. So if I have 1, 0, minus 4 as my vector, we said the 1 norm, the 1 norm is what? The sum of the absolute values of the entries. One thing we often forget is forget to take absolute values. In this case, if we forget to take absolute values, we violate one of the conditions. We get a negative 1. So the 1 norm is 1 plus 0 plus 4 or 5. The 2 norm is the Euclidean length. So that's going to be a square root of the sum of the squares. 1 plus 0 plus 16 or square root of 17. And finally, the infinity norm is going to be the max of the absolute values. That's an interesting result, isn't it? Because we took the measure of that vector and got 3 different numbers. Okay. But it turns out that there's something called equivalence of norms. Okay. And that has an inequality that tells how they're related. And in fact, if you're computing and you're doing error analysis for a numerical method, sometimes the error analysis you work out by hand is easy to do in 1 norm. The computational is easy to do in another number. We have this property called equivalence that tells us that they're in some ways they're the same, even though they're not numerically the same. They're similar enough. All right. They're also okay. Those are vector norms. For matrix norms, the most common ones are what are called induced or operator or natural norms, meaning they're induced by a vector norm. And the two definitions, say in real space, are the norm of a matrix is the max over all products AX taking its norm divided by the norm of X. And you can show that's exactly the same as just using norms with or vectors with length 1. That's an easy proof. Or should be, actually. I don't know if I could do it in 1 minute or not, but I've done it before. It depends on time of day. All right, so let's get to eigenvalues and eigenvectors. If we're given a square matrix, the scalars and non-zero vectors, we talk about the eigenvalue eigenvector pair lambda x. Okay, that may be a little confusing, but the first thing's a scalar, the second thing's a vector. That's the way it's commonly written. They satisfy the equation ax equals lambda x. That's the most fundamental equation of eigenvalues and eigenvectors. Okay, that's the first thing that comes to mind when we talk about what they are. And we'll talk here about A having being real, but again, this all generalizes to complex. The properties, some of the properties are this. Eigenvalues are unique, or eigenvectors are unique only up to a constant multiple. It's easy to see why those eigenvectors are unique only up to a constant multiple, because if this holds, I can put a constant multiple out in front of both sides, right? And I can, because of the linearity, I can bring it inside. So if X is an eigenvector going with the eigenvalue lambda, and so is Cx for any non-zero C. So that's the first thing. For a triangular matrix, if we have zeros below the diagonal or zeros above the diagonal, we can spot the eigenvalues right away. And the eigenvalues are just the diagonal entries. If I wrote down the matrix, the 2 by 2 matrix, 1, 2, 3, 0, the eigenvalues are 1 and 2. I can guarantee you that. I find the eigenvalues, you find 1 and 2. And the symmetric matrix with real entries has only real eigenvalues. Some matrices have complex eigenvalues, and we'll talk about that. If we have a real non-symmetric matrix, all real entries but non-symmetric, any complex eigenvalue will have associated with it its conjugate as another eigenvalue. And we'll see an example of that. So how do we find eigenvalues? Okay, well, I can take ax equals lambda x and I can get lambda with the identity. I can write a minus lambda x equals 0, same thing, right? And then by the fundamental theorem of linear algebra, that's going to have a non-zero solution if and only if the determinant of that matrix is 0, right? That's what the theorem tells me. So that actually is a polynomial called the characteristic equation. It's a degree n polynomial in lambda, and you find the eigenvalues by finding the roots of that. That's how you find eigenvalues. Remember that from linear algebra class? It just has. I'm not going to write this all out. Maybe I'll give you the answer and see if you can check it yourself. I think I've got it written down here. And sort of in the interest of time, we could come back to it, but how would we start? We'd write a minus lambda I determinant, which would mean what? 1 minus lambda, we just subtract lambda from each diagonal entry. We set that to 0. Remember how to write out a determinant expanding by, say, the first row or first column? That's a key thing to be sure to do is alternate signs, right? I'll take one more step. What would we do? If we expand, and again, being constructively lazy, I'd want to expand by the first row, wouldn't I? In fact, this might not take very long. I'd go 1 minus lambda times the 2 by 2 subdeterminant you get when you take out the first row and column. Right? Then do the 2 by 2 determinant, the main diagonal product minus the other diagonal product, and set that to 0. Work that out on your own if you want. See if you can get, I think I made this one where lambda's 1, 2, or 3. You should get a characteristic polynomial with those roots. If you can do that. Is that ring familiar? Pretty much? Okay, What's this part here again? Just real quick, 4 minus lambda, 1 minus lambda, minus 2. Is that right? Math graduate students, counting on you to help me here. Okay, all right, set that to 0. You should get those 3 items. Okay, all right. Okay, is that okay? Let's talk a little more about eigenvalues and eigenvectors. The algebraic multiplicity of an eigenvalue is a number m if the characteristic polynomial has a term in there with the m product. That's what that means. The geometric multiplicity is the number of linearly independent solutions of Ax equals lambda x, number of linearly independent eigenvectors. Okay. A non-defective matrix is one that has n linearly independent eigenvectors. What does that mean? That every eigenvalue has a separate eigenvector associated with it, has just one associated with it. Okay, so yeah, I stuck the solution on the next slide just to show you this. Do you believe me when I say -1 and -3 are the eigenvalues? Let's check that. A minus lambda. I checked this just to make sure I'm being honest with you. For -1, we'd get what? -3, 1, and no, we'd get -1. I had to pause there. -2 minus 1 is -2 minus -1 is -2 plus 1, which is -1. And 1 and -2 minus -1 is again -1. Okay, what should we get? We better get a matrix that is seaming, right? Matrix that is non-invertible. It has an AX equal B solution where B is equal to 0. That's not 0. And if we plug in -3, you better get one again that the 2 rows there are linearly independent, aren't they? I can multiply the first row by -1, get the second row. Well, here's the solution worked out. So we set A minus lambda I equals 0. We get that characteristic polynomial, lambda squared plus 4 lambda plus 3 equals 0. -1 and -3 are the 2 roots of that. And when we solve it out, we get 1, 1, and 1 minus 1, -3. If you're a MATLAB fan and want to check your work, like I always check my work, especially when I teach a class, the command in MATLAB is to use the eigen command to see what the result is. And it gives me the columns, and the columns of V are the eigenvectors, and the elements of the diagonal D are the eigenvalues. And remember we said that eigenvectors are unique only up to a constant. So for -3, it gave us 0.7071 minus 0.7071. That matches by a constant with 1 minus 1, doesn't it? And what MATLAB does is it normalizes the size. I believe it's the Euclidean size of the eigenvector to 1. If you square 0.7071 and add it to itself, in this case, we get. That's why it does that. Okay. So as I said at the bottom, it scales that. All right, so we covered eigenvalues and eigenvectors. Before we talk about complex space, let's talk about complex arithmetic. And here's that, just very briefly, just on 1 or 2 slides. Again, there's tons of great references on this. I found a nice one. I encourage you to look at this. This is a very nice conference paper. Maybe for an undergraduate math conference or something. No, actually, it's more than that, because the subject of the talk was actually quantum entanglement. Okay, so it's got a lot more than just complex derivatives. That's a good paper. And But from there, I just pulled out some of the results. The complex number z always has the form x plus iy, where x and y are real numbers. If you add two complex numbers, say the x1 plus iy1 and x2 plus iy2, you add the real parts and you add the imaginary parts, right? That's all you do. And if you multiply them, we talked earlier about what happens if you have two matrices with complex entries and you want to multiply them together. We just multiply the numbers in the same way you would have the real numbers. But what's true? You're going to pull out a real part of the result from x1 times x2, but you're going to get another contribution from the real part by multiplying iy1 times iy2, right? That gives you the negative of y1, y2. That's why you get that part in the real part of the answer. And the imaginary part of the answer comes from multiplying y1 by x2, actually multiplying iy1 by x2 and x1 by iy2. That's how you, okay, so you get that result. There's a very well-known formula that brings trigonometry, relates trigonometry to an exponential form where there's an I in the exponent, e to the I theta is cosine theta plus I sine theta. What is this one? E to the I theta equals cosine theta plus I sine theta. There's polar form. Any complex number z can be written in the form magnitude of z times e to the I theta. Which brings back the polar form, right? Z is the modulus. Z is the square root of the sum of the squares of the real component and imaginary component. Theta, there's this geometric representation on the complex plane where you draw the complex, you draw it with the real axis and as the x-axis and the y-axis is the imaginary axis. Theta is the angle in radians between the real axis and the complex. Better way to say that. Between the rays of the complex, or I guess you could say it that way. And you can find theta by one of three formulas. Okay? And I think one thing you have to be careful about where you're at, which quadrant you're in. Check that out. Those are formulas that work. Okay, that's what's called polar form. All right, so back to eigenvalues and eigenvectors again. Suppose I give you the matrix with entries 1, -1, 1, 1. 1, -1, 1, 1. So we look at the determinant of a minus lambda I. The characteristic polynomial turns out to be lambda squared minus 2 lambda plus 2. Okay, and we solve for lambda with the quadratic equation negative b plus or minus third of b squared minus 4at over 2a. And we have a negative in the square root. So we get imaginary lambdas, or complex lambdas with an imaginary term. So what do we do here? Lambda equals either 1 plus I or 1 minus I. But what happened? We do see what we said earlier. We said if we start with a non-symmetric matrix with real entries, we're always gonna, if we have complex eigenvalues, we're gonna get complex conjugates, right? That happened here. Okay, that came out. So let's find the eigenvector. And if I plug in 1 plus I to k minus lambda I get the matrix minus I, or minus I minus 1, 1 minus I to use to solve. And it turns out that the x you get is for 1 plus I, you get 1 minus I. And for 1 minus I, you get 1 I. You get those are what you get. And confirming with MATLAB, make sure my math was right. I work this out. Use the I command in MATLAB again. And that's how MATLAB represents imaginary numbers. Look at it. It says 1 plus 1 times I for the first eigenvalue, 1 minus 1 times I for the second eigenvalue. And do my eigenvectors, is the first column the same as what I got before for 1 plus I? I believe so. All right. I get 0.7071 and minus 0.7071 I, which matches 1 minus 1 by up to a constant, doesn't it? And the other one matches 2. It's always good to check. I use MATLAB. I use symbolic algebra packages when I teach calculus. I'll be honest with you. Those are all great tools to make sure we do it right. Inner product. Okay, so we talked earlier about matrix products on the last slide. The simplest matrix product is actually the product of two vectors. And we'll consider two cases. So that's what we're talking about when we talk about the inner product. We're talking about the product of two vectors where one is a row vector and one is a column vector. So if I take two column vectors, x and y and Rn, and I turn the first one into a row vector, which is x transpose, all I do is I multiply them entry by entry and add up, right? So I take a 1 by n and n by 1 and get a 1 by 1. That matches the way we talked about matrix multiplication. And these are called any one of at least three different things. This is called an inner product. Sometimes you see it called a dot product. Sometimes you'll see x dot y. Sometimes it's called a scalar product because it gives you a scalar as a result. Okay. Okay, and that's the notation down to the right there. Sometimes we'll see angle bracket notation, not to be confused with angle bracket notation and the Dirac notation. Okay, all right, to see any one of those things. But you don't normally see, you don't want to just see x, y right together. Okay, you want to either see x dot y or put angle brackets. Make sure you or write x transpose y. So from Calc 3, we talked about the length of a vector, and we've already mentioned this too, the Euclidean length, and we had the fact that that length is the same as the dot product of x with itself for any real number. We have to generalize that for complex. Okay, it's not just the product. We have to take the inner product for complex numbers is defined as the conjugate transpose of the first times the second. If we take two n by 1 vectors that have complex entries, we take the complex conjugate or the conjugate transpose of the first times the second. So as a simple example, if I have 1 plus I and I for x and 3 and 6 minus 2i, make sure I took the conjugate transpose right for x. I have 1 minus I and minus I in a row, and 3 times yeah, 3 times 1 minus I is 3 minus 3i, and minus I times 6 minus 2i is minus 6i plus 2i squared. And again, we get a scalar, but now it's a complex scalar, 1 minus I, x star y, or x conjugate transpose times y. So in the real case, the dot product is symmetric. The multiplications of real numbers is symmetric. Is that true for the complex case? No, it's not. It's not true. And let's see, back on the previous example I had I had 1 minus 9i for x dotted with y, and if I do y dotted with x, I get 1 plus. Well, that's actually the result. The result is that if I have two complex vectors and I reverse the order, what I get is I get the conjugate of it. Okay, that's the result. X dotted with y is the complex conjugate of y dotted with x. So we just have to be careful about that. All right, let me throw this Dirac notation back at you. So if I take this in the ket notation with x as AB and y as CD, the short ket notation is often done with square brackets in that form with a vertical axis for absolute value sign between them, which is really a bra times a ket. Okay, the bra is the conjugate transpose of the ket, right? Which fits everything we've just said about multiplying two numbers. So in this case, it's going to be the conjugate transpose of x times the vector. Okay, it's just the notation, but the way it's often written is you just have to get used to seeing that to mean that, okay? And it gives me pause sometimes, all right? You just have to get used to it. Okay, yes, it's the same, yeah, it means exactly that. It's just X. If I took these as vectors, it would just mean that. That's exactly what that is. All right, okay. Anything else? Okay, outer product. So this is the second case of how we multiply two vectors. One was the inner product, one is the outer product. And again, using the rules we had for what size matrices we can multiply, I can multiply an n by 1 matrix with a 1 by n matrix. I can take two n vectors and multiply the first by the transpose of the second. And the result is the outer sizes, n by n, right? So if I have 2, 1, 0 and 3 minus 1, 2, and I take the outer product, xy transpose, what's going to get multiplied here now? Row by column, 2 times 3 for 6, 2 times minus 1 for minus 2, 2 times 2 for 4. The last is all zeros, right? 0 times 3, 0 times minus 1, 0 times 2. The standard matrix notation or matrix multiplication applied here, but that's called the outer product. The inner product is called the scalar product because it gives us a scalar. The outer product is not. Yeah, right? Outer product is not. Okay, complex case. If I have two vectors that are like n, two n by 1 vectors that are complex, I do have to take the adjoint of the second one. Okay, I take the complex conjugate. X times the conjugate transpose of y. X times the conjugate transpose of y. And in Dirac notation, the inner product was that form, right? This was the short for a bra times a ket, which together gives you bra ket. The outer product is the ket times the bra, x times y star. So if I start with 1 plus I and I for x and 3 and 6 minus 2i for y, the outer product, whichever way I write it, means I take x times the conjugate transpose of y. So I get 1 plus I times 3 for the 1, 1, 1 plus I times 6 plus 2i for the 1, 2, etc. Multiply all that out, and I get a 2 by 2 complex matrix. Okay. Okay, so again, if this can get confusing, but if we're just talking about standard matrix multiplication, we just multiply it out whether it's real or complex. But if we're talking about inner products or outer products, we have to be careful of knowing when to invoke use the conjugate. They both inner product and outer product in the complex case involve a conjugate. Keep that in mind. Tensors. All right. This is an interesting subject because you see different ways these are used and ways you equate things, and mathematicians differ with maybe some physicists on some of this. But anyway, we said that a vector space can refer to various types of sets. We said I spelled definition wrong, but there's an abstract idea, and that's also true for tensors and tensor products. Frankly, for the most part, you won't need the real abstract definitions, but they're there. And I like the working definition from the DBAI.org website. It said that a tensor is a mathematical object that generalizes the concepts of scalars, vectors, and matrices to higher dimensions. And it came out of that DBAI website because, as anybody knows, taking Dr. Mann's classes and other things and use machine learning, tensors play a pretty important role there in that software, for example, TensorFlow and PyTorch. And you've seen some tensors already. We've seen a zero tensor that's a scalar. A vector is a 1 tensor. A matrix is a 2 tensor. 3 tensors are sometimes characterized as what we call a prism. But we can't geometrically characterize higher order tensors. Yeah, I'm not going to say too much about tensors here. But the tensor product has this notation with the circled time sign. And in the Nielsen and Schwang book, they give this working definition. They talk about it as a way of putting vector spaces together to form larger vector spaces, which is kind of interesting. They give it sort of a more abstract feel. And they also say that the tensor product is very important in physics and understanding multi-particle systems. In Dirac notation, there is an abbreviated form in one of those three ways right there. And I say, terms and definitions vary between sources. Just to give you a heads up, we'll consider an informal version here. And we'll add some formalism if we need it, but I'm not going to talk about tensors. But there is something called a Kronecker product, and sometimes they're used, they're kind of equated. I think a one is more a representation of the other. And this definition would make some pure mathematicians cringe. I'm not really a pure mathematician. But Hidari says the tensor product of an M by N matrix and a P by Q matrix is an FP by N Q matrix. But that goes with the statement from Nielsen and Schwang of forming larger vector spaces, right? Forming a larger matrix. And informally, I think it's okay to think about that. But in general, a tensor product is not the same as a matrix product. And that's important. That's an important idea. And so we'll use Hidari's definition. I think those differences are especially important to entire. If we want to find the tensor product of U equals A, B, and B equals C, D, E. This is basically the product of two matrices, right? This gives you the flavor of what to do in higher dimensions. All right, that's enough for tensors. Okay, I'm not going to refer to that today. Okay, let's talk about probability. We'll get through what we can, and maybe when Reinhold gets here, we'll take a break. All right, and I've got a lot more here than I need. I'll go kind of fast, but I just want to give you the, well, not more than what I need, but more than what I could really cover today, I think. But just here's the basic definitions of probability. Okay, so far we've talked about linear algebra. Now we're going to talk about the second subject of probability, and now we're going to do the filter stage of probability. Okay, so there's a lot to cover. I know I'll need pretty soon. So the basic definitions of probability. Okay. The most fundamental is random variable. It's a variable that has possible values that are numerical outcomes of a random phenomenon. This is a really interesting time to understand random variable statistics, right? I mean, what do we see on TV commercials all the time now? They basically legalize gambling and sports betting, right? So it's all around us. You can't get away from it. But a random phenomenon refers to the case where possible outcomes are known. Like if you're betting on a football game, you know what the outcomes are, but you can't predict ahead of time unless the game's rigged what the outcomes are. And there's a regular distribution of outcomes. Mathematically, distribution is a function that gives us the probabilities or the likelihoods of the different possible outcomes in an experiment. And there's two main kinds of random variables that we'll talk about. We'll talk about discrete random variables, and we'll talk about continuous random variables. A discrete random variable has a countable number of values. The first example you always see is tossing a coin, where you get heads or tails. The second example you normally see is rolling dice. Right? If you have two dice, you're going to get the numbers 2 through 12 as the outcomes. Those are discrete random variables. When we talk about those, we talk about probability distributions, and we talk about probability mass functions that list the possible outcomes. If I have a random variable with range x1, x2, etc., the notation it has probability of x p that x equals xk. Okay, so the properties of a probability mass function are that it always takes the value between 0 and 1. Always takes the value between 0 and 1. For the discrete case, the sum of the probabilities is 1. And the probability for any a in the range is the sum of the probabilities of each x. Okay, two random variables are independent if knowing the value of one does not change the probability of the other one. In other words, if I say the probability that x equals x and y equals y, I can multiply the separate probabilities of each one to get the same thing. If that's not true, then they're dependent. An example of independence is when x is the number of heads in 10 coin tosses, and y is the number of heads in the next 10 coin tosses. Okay, what you get in the first 10 is not the ones you get in the second. Dependent is if I'm growing tomato plants in my greenhouse, and I want to compare whether I use sunlight or fluorescent light. Okay, and then they're dependent. And we can define independence and dependence for continuous random variables as well. I'm going to just name a few of the important distributions. One of them is the binomial distribution. This is the terminology you often see for discrete variables involving the formula for the binomial coefficient and things taking k at a time, right? And if we apply this to tossing a coin, if the coin's weighted, so the probability of heads is some value p between 0 and 1. In the unbiased case, p is a half, but you could have it where you say. And if we toss the coin n times and let x be the total number of heads, it turns out that the random variable x is binomially distributed with parameters n and p with that notation. And the probability mass function for x, it turns out to be that binomial distribution. Okay, that's a very well-known result. And here's an example. This figure displays the probability mass function with n equals 10 and p equals 0.3. What's important to make sure it's correct is that the sums of all those bars should add up to 1, the heights. It's important. And an application of the binomial random variables is n independent coin tosses. And each coin toss can be thought of as a Bernoulli p random variable. And this is the probability mass function for Bernoulli random variable. Okay. If x is 1, we get p. And if x is 0, we get 1 minus p, or p is some value between 0 and 1. Otherwise, we get 0. Those are common expressions we see when we talk about discrete random variables. All right, so let me see where a good stopping place is here. I can go another maybe 10 minutes, see where we're at. Okay, expected value and variance. So these are other very common terms in probability that we'd see in talking about quantum mechanics. The expectation, or what's also called expected value, or mean or average, is one of the most important statistics when we talk about random variables. And if we're talking about discrete random variables, if the range is x1 through xk, the expected value is defined as the sum over the xi's of xi times the probability of getting xi. Okay, this turns out to be a linear. It turns out to be linear, where I can, if I have the expected value of ax plus b, it's a times the expected value of x plus b. And what's important here, it may be a little confusing to see that complicated formula and say that's the same as the mean. But what happens if the probability of getting any x is the same? Right? What do we get? Do we get the average or the mean as we've always defined it? The e in that case is going to just be 1 over n, isn't it? The number there. So we're going to get the average and the mean as we always defined it. But that formula is more general. It could be the case where the expected value varies. So that's why that's the case. The variance often called sigma squared or VAR, I use them interchangeably, is the expected value of x minus the mean that's squared. It's an average. It's always greater than or equal to 0. Okay, always greater than or equal to 0. A small variance implies that the distribution is concentrated around the average. It's a self-descriptive word for variance, right? And it can be shown computationally, or can be shown that the variance satisfies. It can be shown that it satisfies the convenient for computation formula that the variance is equal to the expected value of x squared minus the expected value squared. It's not linear. You can see that because the squares there. But or in the way it's defined. But it does satisfy a couple other interesting properties. When I bring in the standard deviation, it's the square root of the variance. But we'll need to modify the definition of expected value for a discrete random variable to a continuous random variable. That changes. But the definitions of variance and standard deviation remain the same. And actually, the ultimate formula for the variance still holds. All right, continuous random variables. I'll fly through the rest of the slide. Or is this a good time to take a break?
Yes.
It's almost 10:15. Are you ready for a break? Should we, Dr. Mann came in, right?
Yes, after the break and then.
Okay, why don't we take a break and then Reinhold, you can say a few words of introduction and I'll keep going. Is that okay? We take a break first? Yeah. About a 15-minute break, is that right?
Yes.
Okay. All right, get something to eat, take a break. It's okay. Okay. Kind of deep for some people.
Some audience want to share, they want to communicate, okay, if you want.
I'll give you the slides. Yes. The slides? Oh, sure.
They want to.
I'll give them the slides. Yeah, I'll send it to you, okay?
I'm sorry, I messed up your schedule.
No problem, that's good.
I really needed to get that.
Oh, that's more
The
important.
proposal is still on August 6th.
I know it's more important.
No,
Grab some food?
No, I'm good, So I had a question about these audience, are these mostly students?
Most of them are students, yeah, we have a couple of TBAs. We have 2 TBA.
Okay.
We have one several from the Eigenvectors, group of the Hill.
Okay.
But most people are students online, they would be the national scholars.
Okay.
From China and from Spain.
Oh, really? From Spain?
Yeah.
Which one's from?
The Garcia. The one that Garcia. The one is.
Oh, Garcia. Oh, yeah. From the math department.
Yes.
The one I introduced you to.
Yeah.
Yeah. Okay, all right, excellent. Okay, cool.
I'm just gonna make a few remarks,
Sure.
thinking of this, talk about the history, things about machine learning.
Yes.
Yeah,
Yes.
we'll go from there. See if there are any questions.
Yes. Get some drink.
Yeah, good.
I will pause the recording.
Okay. Sounds good.
Can I have your name again?
I'm sorry? Your name is? Chris Cox.
Thank you.
Just want to say a couple of things via introduction, which should have happened earlier, but I couldn't be here when you all started in the morning. I just want to acknowledge the support from NSF for this effort. This workshop is part of a grant which was started in 2019. And it involved a number of people, Dr. Liang as principal investigator, Dr. Gao as co-principal, Hemant Jain, Dalai Wu as co-principal investigators, and also Tony Shellam was a co-principal investigator. He is now at Tennessee Tech. He left about a year ago. So I want to acknowledge that, and also the folks who were involved in the organizing of this, which were the same co-PIs and PIs, but also the support people who made sure you had some food and some coffee and some donuts and so on and so forth. It takes a lot of effort to put a workshop like this together. The workshop is part of the scope of this grant, which has now been in place for almost 5 years. And I think it's coming towards the end of its performance period. And if I look back at the beginning of the performance period, very few people here on campus were thinking about quantum technology or quantum information science. And over the last 4 or 5 years, that has really taken off, and there's a lot of activity there that intersects with artificial intelligence and machine learning. And I think that's the topic of this workshop. And I think it's a very timely topic of the workshop for several reasons. And it's not just the buzz that is out there and the amount of work and thought that number of people are putting into this. It's also an opportunity for everybody who is thinking about this, quantum technology and machine learning, to really think deeply what it means and go beyond the concatenation of words, based on the promise that if you compute with quantum bits that can hold more information than classical bits, you have a chance to do things with large data sets and so on and so forth, and you can solve more complex problems because you can search spaces conceivably in a shorter amount of time. This is all conceptually, it makes sense. There's a lot of hand waving. And I think it's very important for people like you who are maybe already in your career, but most of you are probably still, forging your career and your education, to start thinking deeply about these topics, because the fact is, nobody really has done work with actual quantum computers and big data. That problem has not been solved. That transduction, so to speak, of large data sets into quantum bits has not been solved. And part of that was there really aren't that many quantum bits available in actual quantum computing hardware. I don't want to get off on a tangent. I just want to say that it is important to really take this seriously, what it means to converge quantum technology with AI and cut through the hype and really think about it rigorously, mathematically, and also in terms of the execution and the translation into algorithms and new algorithms. So I'm really glad to see a workshop on that topic here. It's one of many meetings and discussions that need to be had, and I'm glad you all are here. And I applaud your commitment to really getting educated in this area, because there's a lot of, I want to say, maybe not white space, but a lot of gray space out there that you can work on and innovate and really put some mathematical rigor into this, and also translate things then in the algorithmic implementation of those new methods. Because when you stop to think about it, when we talk about, machine learning, neural nets, we're still using the neural net ideas from 50 years ago, 60 or 70 years ago, actually. And so there's a lot of space for innovation. I want to stop here and hope you have a good rest of the workshop. You have another 2.5 days, and I think it's very worth your time, and I appreciate you being here. Thank you very much.
Okay, so we'll pick back up with the probability where we left off. We talked about discrete random variables and distribution functions and the expected value and variance and other standard definitions with those. A continuous random variable, instead of a discrete random variable, it took a finite number of probabilities. A continuous random variable takes an infinite number of values, and the probability of any one value, if it takes a constant value, is 0. So that distinguishes it from discrete. I'll just go like this. Get more noise like we just were. All right. So and I was asked to not roam as I tend to do. So I'll stand in front of the mic here. If anybody sees me roaming, just point and I'll move back. So For continuous random variables, examples of the ranges, you could have a range between 0 and 1, that interval, or A and B, given A and B, or between 0 and infinity, or minus infinity and infinity. Could have any one of those as the ranges, but notice they're all continuous intervals, ranges. So instead of a probability mass function for a continuous random variable, we have a probability density function, let's say f sub x of x. And its units are probability per unit length. Some similar, tying in with physics, which is really what we're here to talk about. So we'll not go into a lot of the calculus needed, but we'll have to have some because we have to use integrals. And the expected value of a continuous random variable, distinguishing it from the case for discrete, is defined using an integral. The integral from if A to B is the range, the expected value, instead of the sum, it's the integral, right? But when you learn integrals in calculus, how do you learn the integrals? You learn those as limits of sums. So this makes sense, that formula. As with a discrete random variable, the expected value is also referred to as the mean or average. And the probability density function always satisfies the property that its integral over the whole range is 1. It has to be 1. There's what's called the cumulative distribution function. A distribution function can be defined for any type of random variable, whether it's discrete, continuous, or a mixed case. But that is the cumulative distribution function. One form is f sub x of x is equal to the probability that x is less than or equal to some value x for all x in the real numbers. Okay, and again, we're not limited to what type of variable we're talking about. Some properties of the cumulative distribution function, it's defined along the whole real line. We have to be careful in the discrete case whether we have strictly less than or less than or equal to. It's always a non-decreasing function, and we can always state the probabilities in terms of that cumulative distribution function. So what are the smallest and largest values it can take? I think they're just 0 and 1. If you think about the definition, 0 and 1. So we said that for a continuous random variable, the probability density function satisfies that its integral over the whole range is 1. And the probability that it's in an interval C to D is going to be the integral over from C to D. For a discrete random variable, we can write the CDF as the sum of the probabilities for a value x where we take the range less than that x. But for a continuous random variable, we define it the same way, but we have to use an integral. And in this case, we integrate from minus infinity to x. Okay, for that case. So again, discrete case involves sums. Continuous case involves integrals. Should glue my feet to the floor here. All right, let's talk about variance and standard deviation for CRVs. So the variance is defined in the same way, the same formula. The variance is the expected value of x minus the mean squared, but it's calculated using an integral now, right? We have to integrate from A to B instead of summing, and it's over the entire range. Some sources define it as the integral from minus infinity to infinity, but in that case, we would cut off when we're outside the range. And we can calculate it using the difference of two expected values, or actually an expected value minus 1 squared. That same formula holds. And again, the standard deviation is the square root of the variance for the continuous case. It's linear again, and again, we have the properties satisfied by the variance and the standard deviation. That holds whether we're talking discrete or continuous. Uniform distribution. It's one for which the probability is constant and over the whole range. And what that means is that if I have k discrete values, the probability has to be 1 over k. I think I've already mentioned this. Why is that? They have to sum to one, right? Okay, the sum of k constants that sum to one has to be, means each constant's 1 over k. If we talk about a continuous random variable, what does that tell us about the probability density function for a less than x less than b, if we're talking about the constant case? How do we figure this out? What has to be true of the integral from a to b? It has to be 1. So what does that constant value have to be? 1 over b minus a, right? Thank you, Jamie. And what would the value be for values outside the range? It would be 0. Okay, good. Okay, so here's a couple of examples. If I have the constant case for discrete, the 3 bars, and they're just three variables, 3 terms. What does the height of each one have to be? It has to be a third, right? Has to be a third. And the height for a continuous random variable for what? It's just the area under that curve. The height has to be 1 over b minus a, doesn't it? So that b minus a times that height is equal to 1. Okay, so that's the case there. And finally, another very common distribution is the normal or Gaussian distribution. These are a couple of quotes from sources. It's one of the most frequently used probability distributions in practice. I'm sure you've seen it. It's probably the most, for the continuous case, maybe it's the most well-studied probability distribution. You see it a lot. The density function, also called the Gaussian function, when there's only one random variable, is that product with an exponential term in it. The standard normal distribution is when we have the variance of 1 and the mean 0. And so here's the density function in that case, and they have that simple plot, which we've all seen. We can find any normal Gaussian distribution by shifting and scaling the standard normal distribution using the mean and the variance as follows. Okay, that's very common. So you've seen that before. Okay, that wraps up the first set of slides. So ready to move on to the second set? Okay, so in an hour and 15 minutes, we've covered linear algebra and probability. All right, so that's good. Let me save this. Save some notes and go to save this. Okay, so here we're in what I call Math Foundations of Quantum Computing 2, session 2. Okay, so here we're going to talk about vector spaces and Hilbert spaces. And I've already made some connections, I think, but we'll make more connections between math concepts and quantum, especially using a set of bullets out of Hidari's book, which I really like. I'm going to actually list that slide twice because I think it really helps connect everything. We'll talk about concepts of orthogonal and orthonormal. Unitary operators play a really important role in talking about quantum science. We'll talk about the ideas of reversibility and completeness. I mentioned earlier, we're going to talk about operators. We'll talk about matrix representations of linear operators, and finally, projection operators. Okay, they play a really important role in this area. And again, I mentioned the connection is made by Hidari. I have like I said, a set of bullets from his book, but here's a quote. Hidari says, one of the central concepts of quantum computing is that a qubit can be represented as a two-dimensional complex Hilbert space. Okay, so keep that in mind. Oh, she's got the mic. Okay, all right. Thanks, Kim. Yeah, I don't mind standing here. Okay, let's go back and just review quickly a few concepts from session 1. And again, I'm assuming the folks off-site can hear me, okay, if I stand here. Okay, Joseph says yes, thank you. So if I take two vectors, say that are like two vectors that are complex. The inner product using Dirac notation is and using standard notation too, is the conjugate transpose of x times y, right? Keep that in mind. And the outer product we said is x times the conjugate transpose of y. All right, and those definitions generalize straightforwardly if x and y I gave them for Cn. All right. Oh, they generalize if n is bigger than 2. All right. So we've also discussed tensors and tensor products. In general, just keep in mind, I'm saying this as a mathematician, tensor products are not the same as matrix products. And we need to introduce some definitions now that formalize the concept of vector space and Hilbert space. All right, I want to give you a little more abstract than you might have expected, but I'll do it real quick. I just have a slide for each one of these concepts. It helped. It was fun to put this together when I first did it, just to get this background. And this is actually out of Hidari's book on quantum science. But the concepts of group, ring, and field are foundational to a formal definition of vector space. And Hidari defines each one of these. And Nielsen and Trang already assume we know what a vector space is. But just for completeness, a set G equipped with a binary operation, say denoted asterisk, is called a group if it satisfies these properties: closure for any elements of that set G, the operation A asterisk B is also in G. Associativity, we can reverse the order or reverse the place of parentheses. As you've seen, for example, in multiplication, we can do A asterisk B first and or asterisk with C, or A asterisk with doing B asterisk C. There's an identity element. Okay, and the easiest thing in each one of these cases is to think of an example, right? If it could be the multiplicative identity, but this generalizes. This has a lot of more general interpretations. And there's an inverse. In simple multiplication, it would just be the reciprocal. But a group G equipped with a binary operation is called a abelian if and only if that operation is commutative. Okay, so we'll refer to that again later. I'm just throwing these terms out because we refer back to them. Then there's a ring. And we'll get to a ring after I give you some examples of abelian groups. 3 of the most common are rational numbers, real numbers, and complex numbers. And again, I found myself in my old notes and things using just not the fancy R for real numbers, using the standard R and C. So take it in context, because already I'm throwing a confusion in here. I use R for a ring in that definition. That's not the real numbers. It denotes a ring. If it's a ring, if it's an abelian group, meaning it's commutative under addition, which has an additional binary operation, say multiplication, that satisfies these properties. Multiplicative associativity, that's a standard associative property, and the distributive property on the left and the right sides. And again, examples of those are the real numbers, the complex numbers, rational numbers, and also the set of integers, denoted often with Z. Okay, you may not be real familiar. These are you've seen these. Yes.
Can you contrast abelian?
Well, it would be one that didn't satisfy that property, right? If you lose commutativity, I can't off the top of my head think of an example, but if you lost that property of commutativity, right? Anyone that does not satisfy, if it's not commutative, it would not be abelian. I can't off the top of my head think of an example, but that's what it would be. For our cases, we're going to assume that it is. We're going to assume that it is commutative, that it is abelian. Okay. All right. Field, groups, rings, and fields. A set F equipped with 2 binary operations, addition and multiplication, is a field if it satisfies these properties. That's the additive and multiplicative. And we have the additive identity of 0 and the multiplicative identity of 1. We have to have a multiplicative inverse. right? For every non-zero element, there's an element denoted, say, A inverse that gives us the identity when multiplied, and the standard distributivity properties. So here's a definition of a commutative ring with unity for which each non-zero element has a multiplicative inverse. Commutative with respect to multiplication, and unity refers to the multiplicative inverse property stated above. Okay, so groups, rings, and fields are kind of fundamental ideas you study in upper level math classes. Some examples of fields, again, are the rationals, the reals, and the complex numbers. Z is not a field. Okay, that's an example we lose multiplicative inverses there. Okay. Before defining a vector space, we need one more concept, and that is what's called action of a field on an abelian group. Again, this is a very formal definition we don't always see, but I'm kind of glad to be covering all my bases here with this. And we'll use even a simpler definition than Hidari uses. And Hidari is a book on quantum science. An action of a field F on an abelian group V is an operation that takes elements A from the field and V from the abelian group and gives an element AV. Okay, Hidari uses A dot V, his expression. You can think of an action, and again, I need to think of things as simple cases. You can think of an action as scalar multiplication of a vector by a number. That's one way to think about it. But again, it generalizes. And the defining properties of an action are these distributive properties. We have A times the sum is the sum of A times each term in V. And we have this, the other distributive property where we distribute with the multipliers. A plus B times V is AB plus AV plus BV. So finally, with all those things set up, we're ready to define a vector space. A vector space V over a field F is an abelian group equipped with an action. And I'll give you some examples, okay, to make this come home. This is very abstract. But the point Hidari makes is that if we have these concepts, we can give a much shorter definition of a vector field than is found in most linear algebra texts. I guess it's kind of a hard call for me whether we want to have all these abstract definitions first or not, but this is a whole nother perspective on it. Here are the essential ideas to remember for a vector space, okay? The essential ingredients for a vector space are the properties, sort of the takeaway from this, that we have to have the commutative property, the associative property, and the distributive property. We need an additive inverse and an additive identity, and we need a multiplicative identity. And the most common definition of vector space, if you forget everything else, is that it's a set of elements that can be added together and multiplied by scalars. That really, if you meet somebody in an elevator and they say, "What's the definition of a vector space?" That's the definition to give. But I just gave you the whole foundation of it. Okay. All right. So again, I'm sure I've convinced you that to rigorously establish that a set is a vector space, it takes a good deal of effort. There's a useful shortcut. If we are asking whether a subset of a vector space, if we have what we know is a vector space, and we want to know whether another subset of that is itself a vector space, all we have to do is look and see if it's a subspace. Okay, that's sort of the good news. A subset S of a vector space V over a field F is a subspace of V if and only if S is a vector space over F. If it's okay. And the shortcut is this. Here's the shortcut. S, a subset of V, is a vector space over F if and only if the additive identity 0 in V is also in S, and if S is closed under both addition and scalar multiplication. That gives you just 3 things to check. All right, just 3 things to check instead of all that whole list of rigorous definitions and background that I just gave you. So let's look at some examples of vector spaces and subspaces. The most common vector space I think I may have already mentioned, I think I did mention this, is Rn. And if, again, if we want to specify again the field, we say Rn over R over the real numbers. And similarly, Cn, the set of n vectors with complex elements, is a vector space on the complex numbers. And I can talk about matrices too. I could talk about 2 by 2 matrices, for example, on R. Okay. Let me give you an example of a subspace. These are vector spaces. These are also vector spaces. Now let me tell you the beauty of that shortcut for subspaces. Let me give you an example of a subspace. So I said Rn is a vector space. Let's look at the case subspace of R3. Suppose I say S is the set of all vectors that looks like this. The set of all vectors with the second element being 0, and A and B. This means A and B are elements of the reals. A and B are real numbers. The question is that a subspace and therefore a vector space? There's just three things to check. We don't have to bring up group strings, field, any of those things. One is the three questions is the additive identity. Is the additive identity in S? Okay, what would be the additive identity for R3? It'd just be the vector of all zeros. And that's what it is here. Yes. That works. That's still there. The second one is S closed under addition? How do we check that? We take two arbitrary elements of S and add them together and see if that's in S. You probably already can see that it's true. Let's suppose we take U equals A0B and V equals C0D. We have to have a 0 on both of them. Is U plus V in S? Sure. Sure, we're still going to get a 0 in the middle, right? So the answer is yes. And finally, is S closed under scalar multiplication? That was the third question. So if C is a scalar, is C times the vector A0B in S? Sure. Why? Because the second element stays 0, doesn't it? Sure it is. Okay. All right. So that's an easy example. Okay. Any questions about that? So subspaces are nice things.
I remember that's the last second row.
Oh, here.
Yeah.
So U is A0B and V is C0D. And the question is U plus V in S? Okay, thanks for asking. Is U plus V in S? Maybe before we distribute the slides, I'll write it out better. Okay. Any other questions about my handwriting? Okay. Okay. I think it's starting to show that I got up at 4:30 this morning to finish my slides. Okay. All right. All right. Okay. Final building blocks before defining a Hilbert space. Okay. All right. So Hidari introduces these concepts before he defines a Hilbert space. A metric or a measure on a vector space we need. We've already defined norms. Okay, that's sufficient for what we need. But another thing we need for a Hilbert space is define the concept of a Cauchy sequence. All right, and here's a very informal definition. There's a rigorous mathematical definition that I won't burden you with. You can think of as a Cauchy sequence as a sequence of numbers whose terms get as close as we like, given that we look far enough. Okay. Okay, and you normally define that in terms of limits, you know. By the time we get to the nth term in the sequence, we can give a rigorous definition, but think of terms getting close enough as we go far enough in the sequence. That's sufficient for us. And there's finally a concept of completeness. Every Cauchy sequence in the set converges to an element in the set. You can't wind up with something outside of that set. It has to be in that set. Now, when we define orthonormal vectors and orthogonal vectors, we'll have a different definition of completeness. Just keep that all in mind too. Again, we have to take things in context. So what was the title of my last slide was final building blocks. Here's the final building block, okay? And this is an axiomatic definition of an inner product. And the axioms are three properties for the inner product in a more general context than we first introduced it. Okay, so here's the more general definition of an inner product. And it applies again to this idea of a vector space V over a field F. It's a binary function on elements from the vector space where it satisfies conjugate symmetry, which we've already seen in the standard inner product. There's linearity, and finally there's a distributive property. Next to distributive property, and finally there's what's called positive definiteness, that we always get a non-negative number when I take an inner product of an element with itself, and it's zero if and only if V is zero, right? That's true. That's true for the inner product defined by a norm. We'll talk about that a little more. The first two properties together also imply linearity in the second element. We could talk about linearity there as well, or linearity in the second argument. We showed linearity in the first, so it works both ways. Finally, Hilbert space. An inner product induces a norm. We won't go into this, but there's a norm induced by an inner product on a vector space by simply taking the square root of the inner product. We saw one example. We saw it with the Euclidean norm, and that's true of the other, like the P norms for vectors. So here's the definition of a Hilbert space. A Hilbert space is a vector space over the field of either real or complex numbers equipped with an inner product. Say that inner product is denoted UV with angle brackets, complete with respect to this norm induced by the inner product. Okay. A Hilbert space is an inner product space with the added constraint of being complete. It's another way of saying what I have in the first bullet. And it turns out, the good news in a way, if you're only dealing with finite dimensional things, is that any finite dimensional inner product space is a Hilbert space. All right. But when you go to infinite dimensional, you've got to be more careful about it. Okay. So here's some examples of Hilbert spaces. Just a couple. I found an interesting quote from a book. One of the most common is Rn, the set of n vectors equipped with the dot product. Rn equipped with the dot product, say x dotted with y, or scalar or inner product as we defined it, equals the sum I equals 1 to n of xi, yi. And the norm that goes with that, which we've already know, is the Euclidean norm is just the square root the sum of, well, I could write x dot x. Or the sum of xi squared, right? Same thing. That's easier. Also, Cn, set of complex vectors. We have to be careful here now. Again, the dot product or the inner product is the conjugate transpose of x times y, right? And here's an interesting quote from a book. This is a pretty standard analysis book. The book by Hunter and Nocturgal. But I thought this was really interesting. They have a book called Applied Analysis. Some of you may have taken a course from this. But they say of several applications, well, the 6.4, their section 6.4 is Hilbert space in applications, okay? And when I learned Hilbert spaces, yeah, I guess at some point I did learn applications because I had to do functional analysis in Hilbert spaces. A question, yeah.
The magnitude x there is that 2?
This number here,
Yes.
that's a subscript. Yeah, thanks for asking. It's a little shifted. It means it's the 2 norm, right? Euclidean norm. Okay. All right. Any more questions? Yes, right there. Well, this is real. In this case would be, you would have to use the complex there, right? We have what? Well, sure. The norm would just be, yes. I can define the norm. The norm for x is going to be the conjugate transpose, right? Times x. It would also be the dot product because we take the conjugate transpose dot product. Okay, thanks for asking. Again, so we can call this, that's the 2 norm if I have the square root of the dot product. All right, good. Okay, so let me, this quote's good. I'm glad for those questions. But they say in their section on Hilbert space and applications, and I think when I first learned Hilbert space in a functional analysis class, we didn't talk about applications, right? It's the same way I think about calculus. I wish we would teach calculus by emphasizing where it really came from or why it came about. But then if you study, for example, analysis of finite element methods, you can't analyze those without using functional analysis and certain kinds of spaces. Okay, but of several applications, what they say, of several applications, here's their quote. The first is quantum mechanics. Which I thought was really interesting. And I didn't have them. I didn't have my analysis class from this book. If I would have, and if I would have read that, I wouldn't have appreciated it nearly to the extent that I do now. Okay, but it's really important. It's interesting that they say that. Okay, that just gives us a connection. So again, you get the idea. There's such a strong connection between math, even at an abstract level, and quantum science. So just to try to sort of sum up what we've just looked at, okay, these Venn diagrams help me. If we talk about groups, rings, and fields as like the Russian dolls nested with each other, and similar with the Venn diagram with vector spaces, the subset of vector spaces is an inner product space, and a subset of inner product space is Hilbert space, right? And but the Hidari connects those diagrams by saying a vector space V over a field F is an abelian group equipped with an action of F on V. Okay. And again, as we mentioned, the good news is the shortcut is that in finite dimensions, an inner product space is a Hilbert space, Okay. But in the infinite dimensional case, you have to do it this way with the subset generally. All right, let's move back again and try to get sort of the big picture from the weeds. Let's get back to the field or the how things are interconnected. I really like this set of bullets out of Hidari's book. And this is sort of tying in what you're going to see more of this afternoon and later on, which is a good thing, which you may be wondering about it. Okay. But Hidari says that a qubit can be represented by a two-dimensional complex Hilbert space. And the state of that qubit is represented by a vector in the Hilbert space. Okay. More specifically, the vectors representing the states of a qubit have an L2 norm. L2 norm is the norm I've already shown you. Okay. The norm I used with this. Okay, that's what I've already shown. The Euclidean norm. The quantum register consisting of n qubits is a 2n dimensional complex Hilbert space composed of an n-fold tensor product. There's tensors, n-fold tensor product of the two-dimensional Hilbert spaces representing the qubits. Okay. I've been asked by a couple of people, by the way, if I would make these slides available. They will be available to everybody for whatever you want to do with them. Okay. Anything or nothing. Okay. Probably find a few holes here and there. Okay. A computational basis vector of the space represents a definite computational state of the qubit. Okay. These are all linkages between the math and the physics. A superposition of states is a linear combination of the computational basis vectors. We'll talk more about superposition and linear combinations. And quantum logic gates are unitary operators. We need to define what those are. Okay. So there's physics, there's math. Quantum logic gates are unitary operators which act on the state space. Unitary operators preserve the norm of the vectors they act on, as we'll talk about. That's where I'm going to get a little proof here and there on you. States are transformed to new states, but not just any vector in the space. Or not, they're transformed to new states. So we can build quantum circuits, at least mathematically, using unitary operators. And a really important concept that you'll hear more about later is the idea of measurement. Has very interesting properties when you try to measure something in the quantum, and it's performed by projection operators. So I'll define projection operators mathematically. I'll give you some ideas on that. So we need to talk about orthogonality and orthogonal vectors. So in calculus, in third semester calculus, we had the concept of orthogonal vectors where we talked about two vectors either that had length 2 or length 3. And what that means in calculus geometrically is that the angle between them is pi over 2. It means they're perpendicular, right? That's what we talked about there. And there was actually a geometric formula for the dot product of two vectors that involved the angle between them. We talked about the dot product, again, real numbers, being u dotted with v. There should be a v here. The length of u times the length of v times the cosine of the angle between them, taken as between 0 and pi. Remember that formula? So any vectors that are non-zero for which the dot product is 0, because the dot product has the cosine, the angle between them must be pi over 2, which makes sense. Okay, we get a 0 dot product. They're perpendicular or orthogonal. But we generalize that idea to two vectors in any inner product space. And we say that they're orthogonal if and only if the dot product is 0. Okay. Again, you can think of it as perpendicular geometrically, but it only really applies in that special case, R2 or R3. But it's hard to think of what perpendicular would be otherwise, but orthogonal generalizes mathematically. And so we can write that in terms of bra and ket notation as saying that that product is zero. That's just the dot product is all that is. A set of vectors in an inner product, if I have a whole set of vectors, say n vectors, they're called mutually orthogonal or also called pairwise orthogonal. If I take any two of those out of the set, take their dot product and get zero, okay? Each one is orthogonal to the others. Orthonormal is a special case of that. Before I get to that, let me give you an example of mutually orthogonal. Just if you take the dot product of A times with B or A with C or B with C, you'll get zero. You can convince yourself of that. That's an example. With respect to the L2 norm, with respect to the dot product, mutually orthogonal. Yeah, I'm getting a little bit ahead of myself, but with respect to the dot product, but an orthonormal set of vectors. Yeah. Now, so this is sort of separate. Orthonormal starts here. Orthonormal set of vectors in an inner product space is a set of mutually orthogonal vectors which also have unit length. In other words, the dot product of each vector with itself is one, because I know that this is true. Right? So we can take an orthogonal set, which was this set here, the set at the top, and make that into an orthonormal set by simply normalizing each vector, dividing each vector by its length. So we'd have to divide the vector A by square root of 2, the vector B by 2, and the vector C by 2. But if we did that, those three vectors, alpha, beta, and gamma, in that case, would be orthonormal. Okay, so orthonormal is a subset of mutually orthogonal. Okay, orthonormal means mutually orthogonal. The length of each vector is one, and unit vectors are really important in talking about quantum science. Okay, and unit vectors are all the vectors on the block sphere are unit vectors. The points on the block sphere all correspond to unit vectors. All right, so here's some more concepts from linear algebra. If we're given a vector space V over a field F, a set of vectors, say U1 through UN, spans the vector space V. This is a concept of spanning. If and only if I take any other vector in V, I can form that vector, I'll call it U, as a linear combination of the vectors in the spanning set. That's called spanning, okay? I can form any vector you give me as a linear combination of the other vectors. And associated with that is the definition of span itself. The span of as a noun is that set of all vectors that can be formed as linear combinations. Right? And we know that this is the standard basis for 3. You give me any real vector with 3 entries, and I can form that as a linear combination. In fact, what do? We just take the actual elements of that vector you give me as the coefficients, right? That's all I do. That's the way to remember this. A vector is linearly dependent with respect to another, or with respect to a set of vectors, if it's in the span. If I can form it as a linear combination of those, it's independent of the set if I can't form it as a linear combination, right? For example, if I take a linear independent set, it means that none of the vectors is in the span of the remaining vectors. That's all that means. A very important concept that we can now define is this idea of a basis. A basis for a vector space over a field F is a set of vectors that are 2 things, linearly independent and that span the set. Okay, that's the basis. They have to be linearly dependent and they have to span the set, which means therefore I can form any other vector out of those as a linear combination. I can do that, but they also have to be linearly independent from one another. That's the basis. So here's 2 points about that. In general, basis is not unique. We have the standard basis for R2 here, but I could also form the basis. I can form any other vector in R2 as the linear combination of those second two vectors. Okay. Now, what is unique is the number of vectors in the basis, and that's called the dimension of the vector space. That's called the dimension. If this number of basis vectors is finite, like for R2 or Rn, that's called a finite dimensional vector space. We've already used these terms without really defining them. We're finally defining them. Otherwise, the vector space is infinite dimensional. Okay. And a common notation for the dimension is you might denote the field, but you might have the field defined by the context. For example, if we're talking about Rn, then the field is normally the real numbers. Similarly, the set of complex vectors, the field is normally taken as the complex numbers. Okay, the dimension of R2 is 2. The dimension of the set of complex numbers is 2. If I'm using the field of complex scalars. All right, so the question is this set 1 plus I 0, 0I a basis for C2 in the field of complex numbers? What do you think? Can I form any other vector out of that? And I've got the answer on the next slide, I think. Here, let's see what I've got. That's what I just asked, right? So how do we answer it? You say, given an arbitrary vector in C2, call it A plus BI, C plus DI, can I find two complex scalars, which really involve 4 parameters, right? And form that as a linear combination and get A plus BI and C plus DI back? How would we quickly answer that? We have how many unknowns and how many parameters to play with? 4 and 4, right? We should be able to solve it. Okay, that's the way to think about it. So the answer is yes. Okay. What's the dimension over the real numbers of the field of real numbers of C2? and if it turns out it's 4, okay, not 2. Because now what am I doing now? I'm using real scalars to find that. Okay, it's a subtle difference, but you have to be careful how you define these things. But normally, when we talk about vector space of real numbers, we'll be talking about the field of real numbers, and for complex numbers, we'll be talking about the field of complex numbers. But you can mix them. Let's talk about the idea of an orthonormal basis. Put together the ideas of orthonormality and the basis. An orthonormal basis for an inner product space V on a field F is a basis for which the vectors are orthogonal and have unit length. Okay, the vectors are orthogonal and have unit length. Mathematically, the vectors would form an orthonormal basis if and only if they're the inner product of any two vectors is 0 unless they're the same vector. In that case, you'd get 1. Right? That's what that means in shorthand. And have you seen the Kronecker delta notation, delta ij? This is the definition of delta ij. Okay, the Kronecker, the quick way to say that: if I and j are the same, you get 1. If I and j are not the same, you get 0. computational basis refers normally to a standard or natural basis. I've already called this the standard basis. And Dirac notation in 2 dimensions, we've already mentioned what those are, the 0 ket and the 1 ket. Okay, so keep all those things in mind. Okay, so here's a connection with what you're going to see later today. Dr. Lee's going to talk about quantum gates. And a quantum gate, which I'll denote U, and I think you'll see why, transforms the state of a qubit into another state. Okay, it has to be linear, so it can be distributed across superpositions. If psi has total probability 1, then the quantum gate applied to that has to have probability 1. And it turns out that the quantum gate that meets these conditions corresponds mathematically to a unitary matrix. I think I've already mentioned that when I listed those rules from Hadari. So let's consider matrices that have complex elements that are 2x2 matrices. By definition, a matrix in C 2x2, complex 2x2 matrices, is unitary if I take its conjugate transpose times the matrix, or the matrix times its conjugate transpose, and in either case, I get the identity. What does that mean? That means that the conjugate transpose is its inverse, doesn't it? Okay. Okay, again, you'll see some people, I think, refer to this instead of an asterisk, they'll use a dagger. Okay, just be careful where you see this. It turns out this generalizes straightforwardly to higher dimensions, where I have n by n instead of 2x2. It's the same thing. And again, as I said, U star is the conjugate transpose of U. Right? Take the transpose of all the entries and take the transpose. The concepts of reversibility and completeness. So reversibility of a quantum gate corresponds to invertibility of the corresponding matrix representation of that gate. And as I've just said, the inverse is the conjugate transpose. The completeness relation, which is always satisfied by an orthonormal basis, is that the sum of the outer products, right, of the entries with themselves, or each term with itself, adds up to I. Okay, that's called the completeness relation, and that generalizes to higher, to more vectors as well. But you have to have the sum of the outer products of each vector with itself equal to the identity. And Nielsen and Chuang talk about this, talk about the outer product representation of a linear operator. Let's go, I'll come back to that. Let's talk about unitary operators some more. So if I take the standard basis in Dirac notation in 2 dimensions, or the vector representations, either one, I need to keep flipping back and forth between those to remember what everything is. Suppose an operator U, some linear operator acts on the basis elements as follows. Suppose it takes the 0 ket and multiplies. It does it by taking A times 0 plus B times 1. In other words, it combines the basis vectors and gives me the vector AB. Suppose U has that property. Suppose it operates on the 1 ket by taking C times the 0 plus D times 1 and gets CD. And we'll see later on that that U has a matrix representation. If I know how it operates on those vectors, I can write down its matrix representation in this form, A, C, B, D, and I'll show that, okay? But if we have a qubit with state, say, alpha times the 0 ket plus beta times the 1 ket, it satisfies alpha squared plus beta squared equals 1, which also means that I can write psi as alpha beta. Let's write this out. U times that psi is alpha 0 plus beta 1. Looks like I'm missing a U out there. Well, I think that's right. And I get alpha times AB plus beta times CD, which is this linear combination alpha A plus BC, alpha B plus alpha A plus beta C, alpha B plus beta D. It must be true, if this is going to work, that the sum of the squares of those entries is 1. And we can write U times psi in this equivalent form. We'll show that U must be a unitary operator. So let's go back and recall matrix multiplication results that we've had before. These are always derived in Indian linear algebra class. AB transpose, the transpose of a product of two matrices is B transpose times A transpose. You simply take the transpose of each and flip the order. If I have, that's a real case. For the complex case, the conjugate transpose of the product is the reverse product of the conjugate transposes. And again, star here is the same as dagger. Keep that in mind. What if I take the conjugate transpose of the unitary matrix times the ket psi? Okay. Well, you get the bra of that term. That's by definition. And so I do what? I take psi conjugate transpose times the transpose of U, right? And that is the bra of psi times U star. Okay, that's the notation we need. We need we need U psi to have total probability 1. And we can write that as an inner product and say that has to be 1. And that has to be true for any psi that has total probability 1. It has to preserve that. That's an important property. So let's consider the matrix form, matrix vector form of this, what I just wrote. It's easier for me to get out of the Dirac space for a minute. So I have the conjugate transpose of U psi with itself set to 1, and that has to hold in particular for all orthonormal vectors. So I'll apply it using the standard basis. If I apply it using the standard basis, what that implies is that U star U equals I. Okay, U star U equals I. So U has to be a unitary matrix, and the operator U associated with the quantum gate that preserves unit total probability must be a unitary operator. Okay, so that's the only way we can do that. How would we get from here to here? I would write psi star U psi equals 1, right? And I think I can multiply both sides by enough terms to pull this out and get that has to equal to the identity. By writing psi times psi star on each side. That's how I would do that. Okay, let's talk more about reversibility and completeness. Let's expand on the material that we've had on a previous slide. So reversibility of a quantum gate corresponds to invertibility of the corresponding matrix representation. For a unitary matrix, we've already said that the inverse is equal to its conjugate transpose. Reversibility is guaranteed. The completeness relation, which is always satisfied by an orthonormal basis, is the following again. And as I said, Nielsen and Chang used to talk about the outer product. We'll show for the dimension 2 case, any orthonormal basis satisfies the completeness relation. And this proof generalizes to arbitrary dimensions. Okay. Suppose the two kets A and B form an orthonormal basis. So for any psi, we can find alpha and beta so that psi can be formed as a linear combination of those two. Right? And if I take the ket A, if I take the inner product of A with psi, I can write that as A times alpha times, I substitute psi in with that form. I get alpha times the inner product of A with itself, plus beta times the inner product of A with B. And why is that alpha? It's alpha because we had an orthonormal basis, right? So A inner product with B is 0, A inner product with A was 1. And I get alpha back. And if I wrote out a similar form for the inner product of B with psi, I get beta back by the same kind of properties. So what I have is that I can write psi as substituting alpha with A psi and beta with B psi. I can write psi as why can I reverse this? This is a scalar, so I can put the scalar after after the vector here. And then finally, I can write, I can factor out this ket, and I have this relationship here by linearity of the inner product. Okay, that's important. And that tells me that this is 1. So it's complete. And we've shown that if the two vectors or two kets A and B form an orthonormal basis, for any ket psi, I can write that with this product out front, or that sum of products. And therefore, that must be equal to the identity, because that's true for all such vectors. And that generalizes to higher dimensions as well. Okay, so I'm giving you a little bit of a proof, hopefully not too much. If we're given an orthonormal basis in n dimensions, say with n elements there, this is a generalization of what I've done for 2. Okay, it generalizes so that the sum of those outer products is equal to the identity. It can be shown that any two states corresponding to opposite points on the block sphere form an orthonormal basis, for example. Okay, and that's a useful result. All right, let's go back to linear operators and digress to clarify some terminology, because the whole idea of linear operators is really important. A linear operator is a function, for example, t, that takes elements from one vector space into another. Say I have v into w, that is linear with respect to the inputs. The standard notation is as written there, t colon v into w. You'll see the word operator, the word function, the word transformation used interchangeably. Okay, saying t is a linear operator on a vector space V is equivalent to saying t takes v into V. We only have to specify one vector space. If we're given a linear combination of elements in V, and we want to write it using Dirac notation, with that sum expressed as linear combination, we can use linearity again to take the t inside, as I've done there. And now let's go to matrix representations of linear operators. And every linear operator has an associated matrix representation. And some sources say they're equivalent. If we want to be a little more precise, the matrix representation actually depends on the basis being used. In general, if I talk about a linear operator from an m-dimensional space V to an n-dimensional space W, I'll be talking about V and W having bases, say V1 through Vm and W1 through Wn. And let's suppose I take W, that's the result of taking T times the Vj. Since W is in that vector space W, we know it can be written as a linear combination of the basis elements in W. And we know that the coefficients are associated with the Vj's. we'll let Aij equals, we'll call Aij equals Ci, whatever I and j are. And now we'll write W as the sum of the Aij's times the basis vector Wi's. And the terms, the Aij terms, are the entries of an m by n matrix A that represents T. Okay, so we've gone from this more abstract concept of a linear operator to a matrix. That's what we're trying to do here. And how do we pull that out? How do we quantify that? So that's a convenient scenario is if I'm going from one vector space into itself and I have an orthonormal basis for it, okay? And we can use the completeness relationship and linearity. So I'll write, we know that this is the identity. That's why I can write this here. I know that this is the identity. So I haven't changed anything. But what I'll do is I'll rearrange terms. I've taken this and I've combined these terms now, right? Brought that inside the sum. And I've flipped this over since that's a scalar, right? It may be kind of hard to see at first, but actually this is a scalar. If you want to think of it in matrix terms, it's like a row vector times a matrix times a column vector, right? It's like a 1 by n times an n by n times an n by 1. All right, so I can rearrange those order, but this gives us the coefficients of the matrix representation. These are the Cij's or Aij's, we'll call them. So that's how we go from a linear operator to its matrix representation. Okay, so suppose a linear operator acts on the standard basis elements in 2 dimensions in this form. Again, going back, it takes the 0 ket and forms A times the 0 basis ket plus B times the 1 ket. And it takes the 1 ket and turns that into C times the 0 ket plus D times the 1 ket. And we'll start with V1 and V2 as the 0 and 1. We can find entries of the matrix representation for T using that equation and involve that product and the orthonormality of the basis vectors. And it turns out in this case that we can just write that all out. And again, using the orthonormal idea was here, this is because 0 and 1 are orthonormal, right? That's why we get A. And again, what's the same reason in every case? That's why we pick out C and then B and then D. And it turns out that matches the matrix that we had on an early example about 10 slides back. That gives us the entries of that matrix. So if we had this defined in that form, only in that form, without really knowing what it is in terms of a matrix, we could it turns out the matrix are just those the matrix elements are just those coefficients. If we have a more general set of vectors on the left, for example, it won't be quite as obvious. Okay, but this is the process by which we could do it. Okay, let's talk about projections. Projections. Again, I like to start with something I know and have seen before, and that's the idea of a projection and multivariable calculus. So this may look, hopefully this looks familiar to you. If I have 2 vectors with their initial point at the same location, the vector projection of B onto A is a result of dropping the terminal point of B down onto the vector A perpendicularly. Remember that? How to get a projection? It's like shining a light straight down and looking at the shadow. That's the projection. And the formula that's won't be derived here, but it's derived in a Calc 3 course, is that we can use the dot product and the norms to find the projection, right? One thing to check is make sure everything there is what it's supposed to be. Is everything there? Do I have a vector, right? Yeah, this is just a normalized vector, A over its length, and it's multiplied by the scalar A dot B over the length of A. But the idea again is that the definition of projection we considered in calculus, whether we're talking R2 or R3, extends to higher dimensions. You can't draw it, but you can talk about it. And you can even talk about it in more general vector spaces too. Right, let's consider the vector C shown in the diagram, defined by the equation C equals B minus the projection of A, right? What do? We take the projection of A, turn it around, attach it to the endpoint of B, and see where that ends. And that ends where C is, doesn't it? Okay, remember that? But also we know that the sum, we can see right away. I can move C over to here, can I? And write C there. So the projection of B plus C gives me B. Now, if A has unit length, this bigger vector A, then the formula for the projection onto B becomes A dot B times the length of A, based on the formula on the previous page. If I just have to drop those lengths. And these concepts and results that were introduced in multivariable calculus generalize straightforwardly to a Hilbert space of states represented using Dirac notation. So projections play a really important role in here. So let's talk about it. Let's bring it into the Hilbert space room. Suppose that a set of vectors V1 through Vn or kets is an orthonormal basis for a Hilbert space V. The completeness relation for these vectors we know involves a sum of outer products, right? Actually, a sum of matrices formed as outer products. And suppose we apply the operator represented by that outer product to an element in V and then rearrange terms. Okay, so now we have what we wind up with from this outer product times V, or this to this inner product times V, right? Times VI. It's the inner product of VI with V times VI. In other words, it's a projection. It's a projection. Let's go back and make sure one thing. We talked about orthonormality. So we're talking about length 1. So that works with what we've just talked about. So the operator represented by the matrix, this outer product, is an example of a projection operator. It's actually a projection operator. In this case, in the direction defined by VI. Okay. In practice, it's convenient to refer to the matrix itself as a projection operator. So here's some properties of projection operators. In session 1, where we talked about the fundamental theorem of linear algebra, later on, there's some properties right below that where we said the rank of a matrix is equal to the dimension of the range of the matrix. That's by definition. It turns out that the projection operator has rank 1. This projection operator defined by the outer product of VI with itself. Projection operators of higher rank can be constructed as sums of rank 1 projectors. If I have two values I and j, I can form the sum of outer products and have a rank 2 projection operator. Okay. The dimension of the range is 2. Applying this operator to V, to a ket V in the vector space V, results in a linear combination of 2 orthonormal vectors. And the resulting projection is in the subspace of V spanned by those 2 vectors. Okay, we're back to subspace again. If you project V onto the full Hilbert space using all n basis elements, the result is V. Here's some more properties. If P sub I denotes the rank 1 projector operator given by the outer product, P sub I, where VI comes from a set of n orthonormal basis vectors, then that PI for any I satisfies the fact that it's if you square it, you get it back. That's by definition idempotent. Okay, that's what that's called. If you multiply PI with PJ, you get 0 if I is not equal to J. And if you sum the PIs, you get 1. That's a completeness relation. Which we can see that's going to give us the completeness relation. The first two properties follow directly from orthonormality. And projection operators are a subset of operators known as Hermitian operators. Okay. All right, so these are all important terms. Now, for a linear operator A on a Hilbert space V, the adjoint operator or Hermitian conjugate or Hermitian adjoint, and I'll use dagger notation, is the unique linear operator A dagger, and mathematicians would use A star probably, which for all vectors in Dirac form, V and W satisfies, if I take V inner product with A times W, that's the same as the inner product of the adjoint of A times V with W, okay? And it's important that that's a unique linear operator. And as I said on a previous slide, we'll use A star interchangeably with A dagger. But if A satisfies this property that A dagger or A star equals A, it's called Hermitian or self-adjoint. This is the phrase I'm more familiar with. A normal operator, and these are all extensions of matrix definitions. A normal operator satisfies A dagger A equals A dagger, and Hermitian operators are also normal operators from the definition. Okay, there's an important concept in eigenvalues and eigenvectors called diagonalizable. And an operator is a normal operator if it is diagonalizable, which can be defined for operators, but we'll define it. Let's back up and just talk about matrices. That's okay. A matrix A that's in the set of complex n by n matrices is diagonalizable if there is an invertible matrix V and a diagonal matrix D, also complex n by n matrices, so that D equals V inverse AV. Okay, D equals V inverse AV. And important thing to realize from looking at this, what if I multiply both sides by V on the left? I get V times D equals AV. What does that look like? We're back to eigenvalues and eigenvectors. Okay, all right. And it turns out that A is diagonalizable if and only if A has n linearly independent eigenvectors, which means that in fact is the eigenvector matrix. It has to be invertible, which means its columns have to be linearly independent. That turns out to be, that's the matrix form of AX equals lambda X. Okay, with D having the eigenvalues on its diagonal. And that's what that's really where we're going here too. So if I write AV equals V times D, they have to be equal to each other column by column. Column J of A times V by definition is A times column J of V. Similarly, we get V times column J of D. What did I just write? On a previous slide, I said there's a relation with the eigenvalue eigenvector relationship, and that's it. That's that AVJ. But let's write this as let's let VJ column J of V. I've just got AVJ equals, let's call this TJ. AX equals lambda X. Okay. So they form the eigenvalue eigenvector pairs of A. And there's another important concept here called spectral decomposition. For a normal matrix, we can in fact write A equals VDV inverse, which is referred to as a spectral decomposition of A. All right. Hermitian matrices, and therefore any matrix representation of a projection operator, has some really nice properties. The eigenvalues are always real, And they can, and the eigenvectors can always be chosen to form an orthonormal basis. Okay, so it's worth dealing with those. And it turns out that they often are what we are dealing with. Some more properties of projection operators. In terms of operators and using Dirac notation, if we know the eigenvalues in an orthonormal set of eigenvectors, for a Hermitian operator A in a Hilbert space, we can diagonalize it. We can write A equals the sum of lambda I times the outer products of the VI's. A positive operator A on a Hilbert space V is one for which this product, this inner product, which is also written in this way, is bigger equal to 0. That's a little funny because it really looks more like non-negative to me, but that is the definition of positive. But if it's positive definite, maybe definitely positive, it's greater than. Okay, so these are just the definitions. Two final comments. The eigenvalues of a projector are always either 0 or 1. Projectors represent physical properties of a quantum system that can be either true or false. And the property corresponding to a projector P is true if the physical state psi of the system is an eigenstate or an eigenvector. Those are used synonymously of P with eigenvalue 1, and false if it's an eigenstate with eigenvalue 0. Okay, so again, we're tying together the quantum science ideas with the math ideas here. Okay, okay. My last slide is my parting thought. Let me one more time. I have 2 more slides, and amazingly, guess I'm finishing on time. Once more, I just want to read through this Hidari's statements. A qubit can be represented by a 2D complex Hilbert space. Yeah, I just really like this because this ties together the physics with the math. The state of the qubit is represented by a vector in the Hilbert space. The vectors representing the states of a qubit have a L2 norm or Euclidean norm of 1. Okay, those are all on the block sphere, for example. The quantum register consisting of n qubits is a 2n dimensional complex Hilbert space composed of the n-fold tensor of the 2D Hilbert space representing the qubits. A computational basis vector of the space represents a definite computational state of the qubit. A superposition of states is a linear combination of the computational basis vectors. We talked a lot about linear combinations. And you'll hear more about superposition. That's an important concept. I've just skimmed very lightly the real physics behind all this. But quantum logic gates are unitary operators. That's why they're important. Unitary is important, which act on the state space. And remember, the unitary operators preserve the norm of the vectors they act on. Okay, so they give us new states. They don't just give us any vector. And so we can build quantum circuits using these unitary operators. And measurement corresponds to projection operators. So those are all things just to watch for as we go forward and learn more. Okay, and the final thing that I used ChatGPT to help me with this. If I hit the right button here, this is my final thought. Okay, I took 2 years of Latin but forgot all of it. But I asked ChatGPT to translate "I am more a student than a teacher," and that's magis discipulis quam magister sum. Okay, but that's partly what I love about this, right? There's always more to learn. Okay, and that's also what excites me about just being in this environment. So if you want to keep learning, keep studying this field. There's always more here for you. Okay, all right, and that's very much where I'm at today. I hope I don't feel like I've dumped a lot of knowledge on you. I hope I've pointed you in directions. I've given you references. I've given you terms that at some point you should be familiar with and keep looking for. You'll see these come up in the rest of the lectures over the next 2 days. Okay, so just keep watching for that. And if you want to look back up a mathematical definition, you can find it here, or I'll help you point to other places. You've already seen some of the holes that I have. I'm not a group theorist, for example, and other things, but I'll keep helping you find those answers and keep looking for them myself. Okay, thanks. So what's next? You lunch? Oh, questions? Oh, sure.
Louder, your question.
Yeah, I'll take questions.
Yeah, because we have online, this is all.
The only thing between me and lunch is your questions, but I'll answer any questions. Okay, go ahead. Oh, take a screenshot? Oh, yeah, you're welcome to do that, but I'm gonna send the slides out. All the slides are go to the distribution list. Okay, make sure you sign that sheet or that you register.
Yes.
Yeah, but
We will share
it's like the slides that go out, the registration list is back there. Okay, okay, yeah, sure. Any other quick questions? You can grab me at lunch and say it in lunch.
Okay, thank you.
Okay.
Thanks. Now it's lunchtime now, right?
Yes,
I have not checked yet.
yeah, that's what's on the schedule. Yeah, the schedule has lunch break from noon to 1.
Yes.
Yeah.
Thank you.
Yeah,
Very exciting.
it's interesting stuff.
Yeah, cover more than in class.
Yeah, I did. I had some old notes on probability,
More content science oriented.
a little bit more. Yeah. There's a lot more.
Yeah, I
There's
like
just,
it.
there's just so much here. Each time I do this, it'll get a little better.
In the past, we do not cover the completeness, right?
I didn't, I made up some handouts that I didn't cover in class. I called it like lecture 13.5.
Uh-huh.
That's what that part was from. It was from a whole nother, there's almost 2 more lectures. Okay, there's so much there.
It's very exciting.
It's interesting stuff.
Yeah, you make it, my life easier now, and I don't have to talk about measurement now.
Well,
Right.
you can clarify some things that I did. You can correct some things that I did probably.
Thank you.
Yeah.
Exciting.
It's good. Fascinating field. Yeah. Lot of neat things here. Yeah, it was good. Yeah. This is a really
Very exciting.
interesting area.
Like it.
Yeah, we're very fortunate to have Reinhold, pushing this for us and EPP wanting to do this stuff. I think we need to do whatever we can to make hay out of it and get our students pushed through it. We could put UTC on the map. I think it could.
Yes.
It's really interesting.
Thank you.
Yeah. I hope it helps. Okay.
I have to just pause the.
Yeah, pause the thing. Yeah.
Can you hear me? Yes, okay. Good.
Shall we get started?
Do you want to introduce me?
You can.
All right, shall we get started? Okay. All right, so Dr. Liang, you want to introduce me, or I will do that for myself?
Do yourself.
Okay, so, all right, good afternoon, everyone, and my name is Chancellor. All right, this is for the online attendance purpose, okay, it's not for this in-person auditorium. I don't know, it's rumbling sound. So, all right, I hope it's not disturbing you too much. Anyway, so my name is Tian Li, and I am assistant professor of physics here. I joined UTC 2 years ago in 2022, August. So it's almost 2 years from now. And I'm leading the quantum networking research here at UTC. I have 2 labs. One is in the Ruby, which is for the quantum sensing, and one lab is right there around the corner. And DRB 110. It's for the quantum networking, which is the specialty of the whole city of Chattanooga. You know that we have the fastest internet of the, I should say the whole world. I see the logo actually on one of the vans we drove through my car. I saw like the world's fastest internet infrastructure here in downtown Chattanooga. But you know, it's debatable. It's either Munich or Chattanooga. But anyway, we're one of the fastest. So we have this really good infrastructure, and we build a quantum network, not we, 2 industry companies. The 2 companies build an infrastructure on top of the quantum network on top of the infrastructure here in downtown Chattanooga. So UTC is a big part of it. So that quantum node lab is for that purpose. So, and that's on the research front. Okay, on the education front, we have a certificate program, and this workshop is also actually will complement that certificate program. We have 4 courses, and the talk that I will give to you is based on that one of the course. Okay, we just had that course in the spring semester. That's called Introduction to QIC. Okay, we're gonna have the second one, the third one, the fourth one the second one in the fall semester, and then the following spring and fall. Eventually, those 4 courses will be comprised into 2 semesters, 1 year certificate program. Okay, we're aiming to train to upscale professionals, you know, not professionals, like training who are interested in the quantum QIC applications, and the quantum now is a big thing, so it's good to know, you know, what is quantum, what it's about, and really appreciate it. All right. Okay, so let's get started. So you're gonna be with me for 2 sessions, all right? This session and the session following the coffee break, and then tomorrow morning. So it will be like 24 hours and 50 minutes. I hope it's gonna be a fun journey, but since it's quantum, so it will be not that fun by nature. So bear with me. All right. Okay. All right, let's get started. So this is the outline for this 4 sessions, not for this one. All right, you won't get this much stuff in just an hour and a half. They're going to be distributed in 4 hours. So 4 thrusts of 4 main contents. The first one is the single qubit, quantum information, single qubit, and then there's a second section, multiple qubit, and then the third one is quantum protocols. After you know what is single qubit, you know what is superposition. Once you know what is superposition, you know what is entanglement. And once you know this multiple qubits, we'll talk about entanglement there. Once you know superposition and entanglement, you will appreciate these quantum protocols. Okay, and after you're done with quantum protocols, I will talk about quantum algorithms. These 2 probably will be reserved for tomorrow. At least the last one will be for tomorrow, quantum algorithms, where you can get quantum advantage. Really, those algorithms really shows quantum advantage, quantum supremacy. And I don't have too much time to cover those famous quantum algorithms. Now, but at least I hope I hope I have enough time to cover Deutsch-Holz algorithm and the Gruber algorithm and the Bell inequality test. Okay, which is awarded 2022 Nobel Prize. All right, so let's get started. So the first one is quantum information for single qubit. So those are the topics will be covered in that section. which is superposition. And then the measurement comes with superposition, because that's actually really counterintuitive. Once you have superposition, the measurements will be different than the classical world. And then there's physical qubits. What people have been done to build the qubit, you're using physical systems, all right? There are different platforms. There are many platforms. They're in parallel, and so we should be. I'm gonna give you an overview of those platforms that used to build qubits, physical qubits, and then the block sphere mapping. And this is for you to help you to build this intuitive or pictorially understanding of the single qubits. Okay, block sphere mapping. And lastly is quantum gates, the quantum operation. That's single qubit quantum gates for operating on the qubit, so molecular qubit. All right. So superposition. 0 or 1. You know this pretty well, right? We can have 0 or 1. There's not really a question mark there. There should be 0 or 1. Or right? Now superposition, qubit is built upon superposition, right? You don't have 0 or 1, you have 0 and 1. Is that right? You have these two states simultaneously. 0 or 1. Are you familiar with this? I hope so, after 3 sessions. What are these notations? What are this? 2. This is bracket notation, right? This is 0, 1, what does it mean? Mathematically, what does this 0 vertical bar and left pointing arrow, right pointing arrow, what does this mean?
1 0.
Yes. You calculate in the product there, but what does this 0 mean, really?
As my present will choose 1 0, right?
That's, first of all, physically that means the state, right?
Yes.
You label the state 0 1. You can put a letter there, like up Q, down Q, right? You can on and off. You can just make it here on and off, vertical bar and arrow. Mathematically, those are the vectors. I have some students in my class here, sitting here. All right. Good, so they are vectors, okay? So now you should think of them as vectors, all right? Don't say like, oh, that's a beautiful notation, and this 0. Then you have to subconsciously reflect to the vector. So 0 is a vector, 1 is a vector. And what is the purpose of this vector? Of these 2 vectors, I should say. Orthonormal, right? In a product of 0, 0, 0, 0.0 should be also normal, orthogonal and normal. So that should be 1. 0.1 should be 0. Yeah. So we will have this one for 0 and 1 because they're in a superposition. And we will introduce block sphere because there's 2 states. So we can use a sphere. One is for the North Pole, one is for South Pole. And any superposition of 0, 1 can be mapped on that block sphere. Okay? All right, so that's why we have this superposition. So that's a block sphere. I hope you now agree with me that we have a superposition. I don't want to spend too much time like why we have superposition, but you have to take it as a fact. In quantum mechanics, we'll have 0, 1 simultaneously. Okay? But since there are 0, 1, there are 2 distinct states that are also normal. So we put 0 on the north pole of this sphere, of A sphere, and then we put 1 on the south pole of A sphere here. And we call this sphere called block sphere. Okay? And the radius of the sphere is 1, because it has to be also normal. So normalization is 1. Okay? So any point on the sphere denotes a cubic state. Any point on the sphere denotes a cubic state. Yes. So if you think of like a point here, on the source pole, the qubit is only in 0, right? If a qubit in that's north pole, and then the south pole, and you will have the qubit is only in 1. How about that's easy, right? That's labeled as 0 and 1. How about the qubit in the equator? It's on the equator. What if I have a point on the equator? That's the equal superposition of 0 and 1, right? Because you go from the equator to the north pole and to the south pole, they're equal distance, right? If any point in the hemisphere, in the northern hemisphere, you are closer to the north pole, but you're further from the south pole. Yeah, so I will get into that complex issue later. Okay, that's the phase issue. But now it's just for you to build up this intuitive picture of the superposition of 0 and 1. It's a block sphere. Okay, everybody cool with that? Okay. So if you write down the superposition like this, 1 over square root of 2, 0 plus 1. This is the superposition of a qubit. This means, like I said many times, the qubit can be in 0 state and in 1 state. What is the coefficient? What does the coefficient mean? 1 over square root of 2 there. Do you know that? What does the coefficient of 1 over square root 2 means? It's the probability amplitude of finding 0 or 1. It's not probability, it's probability amplitude. Okay, so if you get square root of, if you square root of 1 over square root of 2, what do you got? 1 over 2. 1 over 2 means 50%. Okay, so in this state, that means you are likely, very likely, 50% you got 0 and 50% you got 1. Like flip a coin. 50% you got head, 50% you got tail. Right? So that's amplitude. I'm actually reviewing the mathematics for this the bracket notation, Dirac notation, the bracket notation. Okay. All right. So for this one, it's on the equator. Like I said, on the prior slide. So this one is on the equator because it has equal distance from the to the north pole and to the south pole. Okay. All right. Probably should go faster. All right. There are many others. So for some other states, so the equator will have this equal probability to find 0 and 1. But it doesn't prevent me from writing the state like this. 1 over square root of 2, 0, minus 1. Right? Minus 1. As this graph indicates that this point is actually right here, right? Down there is to the opposite. So this x-axis is pointing us. On the back of the axis, you have this point. This indicates the state is there. So what's the difference between this point right here? If you take a look at the prior slide right here, this point. Now axis is here, right? The point, the black dot, is right here. Now the black dot is here. What's the difference between these two black dots? If you just draw a coordinate, x, y coordinate, what's the difference on the x, the positive x and the negative x? If you know the complex number, I assume that you all know complex number. What's the difference? If a point is on the positive x-axis, a point on the negative axis, what's the difference? Phase. Thank you. The phase is different. Okay? The phase is different. This is probably why the quantity is so fragile. if I give you a state, I give you 2 points. One is on the x-axis here, right here, the point on the prior slide. Another one here. I don't tell you the phase. I want you to measure 0 and 1. And I guarantee you gotta see that's the same state, right? Because you have 1 over square root of 2 square of that is 1 over 2, 50%. You will get 50% of 0, 50% of 1 all the time. You won't be able to tell the difference between these two states. So I need to give you this phase information. And what's the phase difference here? 180, right? So to maintain a qubit, you need to maintain the probability amplitude. You also to maintain the phase, because you will easily get different qubits on the equator. Every point on the equator, if I don't tell you the phase, I want to measure the probability of getting 0, 1, you will get 50%, 0 and 1. You don't know the phase. And phase is really important. Amplitude and phase. Okay? All right. Again, on the equator, on the other side of the equator, okay, the y-axis, you can see here, the point here. Now it's no longer minus. It is what? I. Right? Plus I. And what can you write I to? If you want Euler expansion, I want you to expand I using Euler expansion, what do you got? It's e to the I times a phase phi. And what's that phase phi? Euler expansion. I is equal to, this is running out of ink. I is equal to e to the I phi. What is this phi? Yes, thank you. This I times half of pi. Minus 1 is equal to e to the I phi. What is this phi? Minus pi. Pi, sorry. Right? Yes.
We have online students. We have online people attending.
They were not able to see the.
Can we see?
Oh, I will just.
I can type in the formula.
Oh, no. Yeah. Oh, well, yes, you have time. Yes. Oh, well, this is Euler equation, right? Euler formula. You have the pi and minus pi. I have half pi and minus pi. So you see that if you go from x, you end up here, that's half pi span. And then you from this here to here, you go further, you keep going from this y-axis to the minus axis, and you got pi, which is minus. There, so you have the phase there. All right, this more to here, more to that soon. Okay, the phase is really important. Remember that. Now we build up this intuition. All right, so I will just now this is the fourth one, right? This minus here is I, and this I here and minus I there. Okay. All right, so there's 4 special points on the equator. Each point will indicate different phase, and the phase is actually you could find the phase out using the Euler expansion, Euler formula, now expansion. All right. Now they have names. They have plus, minus. So we have the 4 different states, right? Is this annoying to you? The sound? It's okay, right? All right. Good. So now we have 4 states. Okay, 4 points on the equator. We have same 4 states, right? Let's name it. Let's name that. Reduce the notation, the mathematical notation. Well, I don't want to write down the state all the time along the calculation. Let's name it. Let's name that. Minus, plus, minus, I, and minus I. Okay, so write that down. Plus, minus, 1 over square root of 2, 0 plus 1, and so on and so forth. Plus, minus, I, minus I. Okay, so those are the 4 points on the blocks there. Now, imprint this into in your mind. then we gotta use this repeatedly, okay? And I will not spend any time on what is I, what is minus I, what is plus, what is minus plus, on in the later instruction, okay? We'll just use that. I hope you know that 4 points on the equator. Those are the denotion of the 4 points on the equator, okay? And also remember 0 and 1. 0 is North Pole, 1 is the South Pole. Those 4 distinct points, okay? Now I want to introduce another concept. In a Hilbert space, you know Hilbert space? In Hilbert space, you have those orthonormal bases. Do they fulfill that requirement? This 4 states, 0, 1, 0, 1, plus minus I, are they orthonormal to each other? They do, right? They do. If the Hilbert space is 2-dimensional, we have how many bases here? If Hilbert space is 2-dimensional, we have how many bases here? How many points are here? No.
6.
Including North Pole and South Pole and including the 4 points on the equator, we have how many points we have here? 6 points, right? And Hilbert space 2-dimensional. How many bases are here? If one base contains 2, Hilbert space means 2-dimensional, means like in that base there are 2 or eigenspace. And how many bases we can pick here? 3. Thank you. 3. There are the 3 bases, and they are called 0, 1. As famous as it is, they are called computational bases. Okay? And 0, 1, 0, 1, these 2 states, you can write it down in the spherical sphere, right? The spherical coordinates. You can write it down as 0, 1, 0, 0, minus 1, 0. And these 2 states, there are 2 vectors. Oh, yeah, you agree with me, right? There are 2 vectors there, 0 and 1. So these 2 form a basis called computational basis. Computational basis is written down as 0, 1, and you need to know that 0, 1 are 2 vectors. And these 2 vectors are also known. You can also pick plus and minus as your basis. And you can also pick minus I and plus I as your base, as your basis. 3 different bases here to represent 2-dimensional Hilbert space. Okay? Good. All right. So to give you an example that every point on the equator has a face, and this point here denotes the face, and that represents the face of pi over 6. Okay, so every point equator will have different face. All right, so, and if you move away from the equator, and this is an example of if you move away from the equator, take a look at this point. Or take a look at this state, the cubic state. There are 1 over square root of 3, there's square root of 3 over 2 plus 1 over 2. Right? What is the probability of finding 0? If I give you a state like this, 3 over 6. Sorry, 3 over 4, 75%. What is the probability of finding 1? 25%. So that intuitively that is the case, right? It's closer to 0 and further from 1. So it's easier for you to find 0 than finding 1. 75% of finding 0, 22% of finding 1. Okay? So every single point of the block sphere, and this one is nasty. It is down there in the southern hemisphere. And it has the probability of 2 over 3, 0. So that means if you want to find the 0, you're going to have 4 over 6% of finding 0 because it's get close to 0. It's close to 0. And 1 is there, it's further from 1. Do you know how to calculate that? The modulus of this complex number? I see some nodding, I see some shaking. Okay, I assume you're gonna know this, okay? One is fine, like, this is you. Sorry. So there's a way for you to get the probability, okay, from the complex number. The probability from the complex number. So probability amplitude is a complex number. But there's a straightforward way of you can get a square out of that and find the probability of that. So remember, there's I there, okay? Probability can be, the probability is always real, positive, real. But the probability amplitude is complex, okay? And complex means what? Why would we introduce complex number? No, not really like that reason. Not really that. So imaginary, why would we introduce imaginary number? We want to introduce a phase information there, right? Right here. Right? We know I here represents a phase of 2 pi, a half pi. We want to know the phase information. Okay? So that's why we introduce the complex number for the probability. Okay? On cubic, now, if this statement there is red, tilted, and bold, that means that's the take-home message. So a cubic on my slides, that's my if you are sitting in my class where students knows that, okay, this is the most important thing for this whole class. So cubic can be any point on the block here. All right. So that's all right. I'm going to the measurement. All right, you know the superposition, right? You know the probability amplitude, which is complex number, and you know any point on the block sphere is a state. Okay, and let's introduce the measurement in the quantum world in a rigid way. Okay, I actually briefly mentioned that if you measure that state, you got 50%, you got 50% of 1, of 0. But let's study that in a rigid way, rigorously. Okay. All right, the second subject is measurement. Measurement in the Z basis. What is the Z basis? I haven't introduced the Z basis, but this is really suggestive, right? What is the Z basis? It's a vertical basis. It's 0 and 1. It has the null spool and south spool. It's called the computational basis. Okay, and computational basis, you write that down as too long. Computational basis. Let's just name it Z basis. Okay, so that's the basis. All right, measurement is the basis. So if we have a state of 0 and 1. Well, no, sorry, we have a qubit. That qubit has the 0 and 1 state. Okay, and if you measure, let me ask this question. What if I give you this really simple state, which is 1 over square root of 2, 0 plus 1, and I want to do the measurements. I give you a lab report and you want to write down the result. What do you write down there? You do one measurement, what's the result? It could be 0 or it could be 1, right? It's 0 or 1. And then when you do the next measurement, you write down 0, and you do the next measurement, you write down 1. And when you do the measurements million and million times, you got 50%, half million times almost, you got 0. Half million times you got 1. But for every single measurement, you got what? You got 0 or 1. You don't get 0 and 1. Okay? So for measurements, for quantum measurements, if you don't get any information, like if you want to do the measurement and you get any information about the states, you don't do it once. You don't do it twice. You do it many, many times. You do it in a statistical way. Meaning that you have to prepare this qubit. You measure one, you prepare one qubit, you do the measurement. The qubit is gone. It's 0 or 1. You measure another qubit, it's gone. Imagine another qubit is gone, and you have to prepare millions and millions of qubits, the copies, millions and millions of copies, and then you know that, oh, I prepared 1 over square root of 2, 0 plus 1. Okay? But for each measurement, so now you see that for quantum measurement, it does not refer to one single measurement. Remember that, okay? The probability is given by the known square of the amplitude, which I already said that. And this is bold, this is red, and this is tilde, and you should remember that, okay? Cool? Okay. So let's take a look at this, and we also see earlier, right? And this is a nasty one. Yes?
Could you go back to the previous slide? When we talk about the measurement, now I have a question. According to the current technology, do we need to worry about the noise, or we can just safely assume that we could stay with the probability?
Yes, we need to care about noise. But the noise is actually after you compare the qubits. The measurement itself wouldn't correct. You will see, I will talk about quantum error correction. I will talk about quantum error correction, hopefully today. In the quantum particle, in the second part of the multi-qubit. So the error, noise definitely will introduce error. Okay, but measurement itself won't correct the error. The measurement will give you the information about error, and then you know how to correct it. Okay, so we do care about noise, we do care about the amplitude. So for here specifically, let's use that example here. If I prepare the qubit like this, I want to use qubit to do the computation. What we care about this amplitude 1 over square root 2. We don't want this 1 over square root 2 over 3 to become 2.1 over 3. We want this to be 2 over 3. And then this 1 over 1 plus 2i over 3, we want this to be just exactly that. Okay? We want to maintain the amplitude, we want to maintain the phase. That means we want this point to here exactly on the sphere. If this is a little block, the sphere is like wobbling on the, if this point is wobbling on the block sphere, we want to correct it. And that's the quantum error correction used with. We want this qubit to go back to the point it prepared to be. Okay? Yes. To answer your question, yes, noise is a big issue here, and it's the information about noise is acquired through the measurement. So to get the amplitude, right? You get a probability amplitude. To get a probability from a probability amplitude, you do this, right? So it's 4 over 9, and this one, wow. That's how you get amplitude. Probability from a complex number. Okay, so that's you get a square, and you got that. You use this dot. It's what is this? This 1 over 2i over 3 is itself, and the 1 plus 2i over 3 is what? Is a name. It's called complex conjugate. Right? It's called its conjugate. So you use itself times its conjugate. You got probability. It's 5 over 9, and you add this to. It's 1. 4 over 9 plus 5 over 9 is 1. Okay, so the total probability of finding 0, 1 is 1. Okay. Oh, good. All right. So now I'm going to introduce a state collapse. If we do a measurement, I give this qubit and you measure it, it got either 0 or 1, and it's no longer in the superposition. Right? It's no longer in the original state. And we refer to this operation as the collapse of the superposition. So the state collapsed to either 0 or 1. Or mathematically, this state in the Hilbert space collapsed to its basis. Right? Right? You write it down as 0 or 1. 0, 1, and each you do the measurement, you only got 0 or 1. It collapsed to its basis. Okay? You collapse it. So you want to know the state, you need to do it. If you do it, if you measure it, you need to measure it, and if you measure it, you collapse it. This is the nasty of quantum mechanics. It's also the beauty of quantum mechanics. Okay, you will know quantum no-cloning theory soon, and we're going to take this advantage. Okay. We take the advantage of this the measurement collapse, the state collapse, for quantum communication purpose. Normalization. So I think I can skip this. Right? Like, yes.
Question.
Yeah.
So it will collapse on any basis, any standard basis, or only standard basis, or any pair of the basis?
It's a brilliant question. It's up to you. It's up to you. You have the freedom to pick the basis. And we're gonna have a quantum key distribution session tomorrow. Remember, one of the key protocol, one of the steps on the recipe is for you to pick the basis. Right? Alice and Bob has the freedom to pick its basis, which is hidden from Alice, which is also hidden from eavesdropper. You have to pick the basis. You have the freedom to pick the basis. Okay? Yes.
Yes, I have one question. Why do you say about the collapse state from the quantum state to the basic state is an advantage? Because for the determinists, we can determine which state that we want. But for the quantum state, we have to measure it, and after we measure it, the state is disappear.
Yes.
Yes.
Yeah.
Why do you call it an advantage?
Because it's disadvantage to you, and it's also disadvantage to the ill-willed guys, to bad intentioned guys. I don't know the state, but I have good intention of maintaining the state. I want the state to be intact. I don't want to touch it. I prepared it. I send it to Alice. Suppose I'm Bob, and Alice sent someone to send the state to me. I prepare it. I take good care of it. And I do the measurement, I have good intention of the state, but the state can also be stolen by a bad intention guy, like eavesdropper. And he could do whatever they want, but they collapse the state. Right? So you will know. More to that later. Okay? Why the collapse is actually a good thing. It's a disadvantage to you and also disadvantage to the bad intention guys. Okay?
Sorry, there's another question on the chat. You can
let me
okay. So
answer the question after the session.
sure.
Right. So normalization, I will skip this. Okay. First of all, do you know normalization? Do you know it? Yeah. Okay. All right. Measure many other bases. Yes, this is. All right, so we call 0, 1 the z basis, and we call plus minus the x basis, and we call this plus and minus I the y basis. The z basis is the simplest one because it contains the north pole and south pole, and it's on the z-axis. And then the x-axis has this plus and minus basis, and the y-axis is plus I and minus I basis. So we're gonna use this basis repeatedly, these three bases repeatedly, okay? In the later in some later slides. But now it's bold, it's red, and it should alert you that this you should remember. You should remember that, okay? So on the other basis, you can measure the qubit with respect to any of the bases, like this statement indicates that you can actually measure the basis. You can measure the qubit on any opposite points on the Bloch sphere, and you call that a basis. So there are three distinct bases. I also list three big famous bases. We call that X basis, Y basis, Z basis. They're not just inclusive. Okay, there are many bases on the Bloch sphere that you can pick from. As long as these 2 points is on the opposite side of the block sphere, and you can use that as your basis. Okay? Any opposite point of the block sphere can be a basis. All right? As long as they are also normal. Okay? All right. So now let's take an example. This measurement, this example can tell you how we do the measurement, and it comes to your question: what if we do the measurement in different bases? Okay, so if we have a cubic in this state, and we do it, we measure it, it's there on the block sphere. Okay, it's on the block sphere. So we do, we can measure this cubic in different bases. We know already, therefore, there are 3 bases: x basis, y basis, z basis. Let's use another basis. Arbitrary basis, like this one here, we can measure this cubic in z basis, 0, 1, x basis, plus minus, y basis, I minus I, and let's just measure the cubic again in a 4th basis, which is a more arbitrary basis. And what these 4 bases, again, you only need to pick the points opposite to the block sphere and call that a base. That's only required. You cannot pick any point on the block sphere and say that, oh, there's 2 points, this is my basis. No. You have to pick the points opposite to the block sphere, on the block sphere, and you call that a basis. Because these 2 vectors are also no. Okay, that's the only requirement. All right. So let's measure the states in the x, y, z basis and on the 4th basis. Okay, let's use this example for you to understand the measurement here. Okay. All right. So first, let's measure this in the x basis. In the z basis, we know that we're gonna get what? We're gonna get 0 and 1, right? Because that's the 2 eigenvectors of the z basis. That's you can only get. We measure the state, we collapse the state into the eigenvectors of the state in the Hilbert space, and we have 0 or 1, right? Now, what if I want to measure, like here, if I give you a quiz, I assign a quiz to you, I have this state here, and I want to measure, the question is no longer, let's measure this state, square root of 3 over 2, 0 plus 1 over 2, 1. Let's measure the state in z basis. The question is now, let's measure the state in the x basis. What's the probability? First of all, what's the result you would expect to be now if I measure the state in the x basis? What could be the results, the measurement results? First of all, that's a simple question. Let's reduce that one to this one. What is the measurement result if you measure this to in the x basis? Positive and negative. All agree? Those are the 2 measurements results. The only 2 measurement results that you can obtain from measuring this cubic is plus or minus, because those 2 states are the eigenstates of this basis, of the x basis. So you can only get these 2 results. Okay. Question is, what is the probability of x, of getting x, and what is the probability of getting minus? Amplitude. We need to get to know the probability amplitude, right? But now this probability amplitude is written in terms of 0 and 1. Can you convert this into the x and the minus basis? Do you know how to do you know the change of parameters, the change of variables, the tree that mathematicians use all the time? If I want you to replace 0, 1 with plus and minus, can you do that? Let's forget about quantum mechanics. Let's just see that. Let's just use 0, and I want you to write 0 in terms of plus and minus. Can you do that? Do you remember the 4 states? The sets of equations that's put there? 0, 1, plus, minus. Yes, we can. Right? So let's do it. We use these 2. Plus and minus, we write down in terms of 0 and 1, and we do the change of variables. Right? We write 0 in terms of x plus, x minus, we write 1 in terms of x minus. What we do now? Now we have this. We're plugging into this one, right? We're plugging here. We're plugging into this equation. Now I refuse to see the state. I see this equation. Plugging into the equation, use the change of variables, and that's 0. That's 1. Do a tree. Organize the equation a little bit. Organize identity. This is what we got, right? In terms of plus and minus. Now, are you able to calculate the probability in terms of x and y? In terms of plus and minus? Yeah, you square that. You square that about that, and you square that about that. Right? So, and measurement, now you see that measurement is not only depends on probability amplitude. If you have to prepare the qubit, you have to tell the other guy what state you prepared. Okay? If you prepare the qubit into the computational basis or the Z basis, it's written in this way. That's the computational basis qubit. And if you prepare the qubit, that's the same qubit in the x plus, in the plus and minus basis, which is completely different than the other one. But they refers to the same point on the blocks here. Right? So if you do the measurement in the computational basis, you got 409, it's 60 something, right? 409%. Now, if you measure plus, you got 93 probability of getting plus, and only 7% got to get a minus. All right. Again, I will skim through. You understand that, I will whiz through. But let's just measure it in the plus I and minus I basis. What do? You do the change of variable again. You write down plus I and minus I in terms of 0 and 1, and then you solve 0 and 1 in terms of I and minus I, and you plug into the equation, and then organize it, and you have I and minus I, and now you have the probability of finding the qubit in I eigenstate or minus I eigenstate, and you square that. Wow, 50%. You see, if you measure this qubit, you have to, if I measure the qubit, I got 50%. If that other guy's professional, he will be really annoyed. I mean, he will not be happy. He'll see, tell me the basis, please. Okay? And then, oh, I measured the basis in the plus I minus I basis. And then it turns out it's 50%. Okay? And the same measurement conducted in the plus and minus basis will go 93% of getting plus and 5% and 7% getting minus. All same qubit. All good? All right, now let's pick a random basis. Or arbitrary basis. Let's name these two bases A and B. First of all, why I can call these two bases, I can call these two states, eigenstates of a basis. Why I can call these two states a basis? The inner product is 0 and orthonormal. It's all because of orthonormal. The inner product of them, these two states, are they 1? In a self inner product, are they 1? Or the cross product, are they 0? Right? Is it 0? They're the same, right? They're not. They will fulfill the requirements, right? So they can be a state. Now you know that if I want to measure the qubit in this basis, what do you do? So change the variables again, right? You write 0 and 1 in terms of A and B. You write 0 and 1 in terms of the A and B. And you plug into the old qubit, and you do the organization, and you got 0 and B, and this is the new state. And you calculate probability and calculate probability, and then you got different ones. Yes.
I have a question. So like with the basis in the Alexander, say it's on the positive space. How will
These two bases are here, right here and here.
they are not in, like say both are say positive. How will you choose the probability? Which
You nature will choose that. You have no. It's not at your leisure to pick the probability. Did I don't know if I answered your question. Did I? Oh, okay. All right.
because we calculate the probability by using A, so that whatever the probability we choose that close to A.
The probability attached to the basis, but the probability attached to the measurement result. And the measurement result can only be the eigenstates of the Hilbert space. And these two eigenstates in this spaces are these two. And which we call that A and we call that B. So either get A or you get B. Okay. All right, so consecutive measurement. Yeah, I will skip that consecutive measurement, block sphere mapping, phase. So we know that the block sphere, to map the qubit on the block sphere, amplitude matters and also phase matters, right? Right, agree? And if you have this, if you write down some qubit like that, like this, you have e to the I theta, and I want to measure the probability of finding 0 and 1, there will be just square root of this probability amplitudes, right? Because both of them have the phase factor e to the I theta. And we call this, well, this theta actually, if the theta is 1, if the theta is pi and a half pi, it won't give the probability difference right here. It actually adds to both probability amplitudes of 0 and 1. So for this one, we call that global phase. Because this phase will have the same effect on both probability amplitudes equivalently. So we call that global phase. It's frozen. Okay. To measure that, you know, you get 75% and 25% of the probability, and this global phase won't change anything. Okay. Global phases are physically irrelevant in circuit-based quantum computation. Right. So this is an important statement, although it's quite intuitively. Okay, it's really important. But this will bring you to another phase, which right here, it's the global phase, and then another phase, relative phase, will be more important, more relevant here. Okay? So what is relative phase? So if we have this, let me just bring this, yeah. We write down the plus phase, the plus state in terms of computational basis or Z basis 0 and 1, like that, right? You remember this, right? And then we write down the I basis, I, in terms of computational basis 0, 1, and that's that. And then we can further write down I in terms of here, I over 2 pi, right? You know that. So this phase is really important, agree? Because if this phase is not half pi, if the phase is pi, you bring the basis to what? To the minus phase, right? So if this is no longer, this is not I, sorry, this is not half pi, if this is pi, and the whole thing is -1, and -1 is plus, it is minus. It's a different state, right? So this phase is more relevant. Okay, so that's the relative phase. So the relative phase is more relevant here, and it's basically just a mathematical extension of complex number. Okay, Because to write down a complex number, you need to know the phase, right? You need the amplitude, you know the amplitude, you also need to phase, you know the phase, so that you can pinpoint a point on the complex coordinate, right? So you need to know the phase. So, all right. Now let's do we know that we use the four special cases. We have 6 points on the block sphere. On the block sphere, we have 6 points, and those 6 points can form 3 different bases, right? And we know that any point on the block sphere is a qubit. Okay, any point on the block sphere is a qubit. That means if your qubit can be written in terms of this generic way, that alpha 0 plus beta I, we should be able to find this qubit on the block sphere. Agreed? Because any qubit can be found on the block sphere, and this is the arbitrary representation of the qubits, and this qubit should be found, we should be able to find this point on the block sphere. When this qubit is written in this way, alpha and beta, right? By how? Right, so this actually deals with that block sphere method. If I give you the qubit in terms of alpha and beta, and I want you to find this qubit on the block sphere, and the way of finding this qubit on the block sphere is to parameterize. Parameterize alpha and beta in terms of what? Spherical coordinates. What are the spherical coordinates? If the sphere, so first of all, these spherical coordinates, what we have there, how many parameters we have in the spherical coordinates? R, theta, phi. What is R? What is R? Radius. What is R here in the block sphere? 1. Why is 1? Because the probability add up to 1, right? So that's 1. So we don't need to parameterize that. That's fixed. So how we parameterize it? So we are left with theta and phi. So all we need to do is just to parameterize alpha and beta in terms of theta and phi, and then we can pinpoint that qubit on the block sphere, right? This is how we parameterize. Again, it's change of variables in mathematical tricks. Using mathematical tricks. Alpha written into the sine half of theta, beta into e to the I5 sine cosine. This is cosine alpha, and then beta is sine half of theta. All right. We parameterize alpha and beta in terms of theta and phi by convention. Okay. All right. Of course, we're gonna restrict the range of theta and phi into pi, 0 and pi, and into the half of 0 and half. That is why theta is actually, you have to put 1/2 up there. And do you know theta and phi on the plot of the spherical coordinate? Do you know that? What is theta? Theta has a name. If I put, okay, so now you know that the qubit can be written in this way, right? It's no longer alpha and beta, and we already parameterized alpha and beta in terms of the theta and phi. So that's 0 and 1. Theta and phi. 2 variables, still theta and phi. And we need to know what it is. We need to find out theta and phi, and then we will be able to pinpoint that qubit on the block sphere, right? So this is a new qubit representation in terms of theta and phi. And I hope you know what is theta and phi on the block sphere. So yeah, let's use the example. Walk through the example. So we give you this qubit here, this one. Right? We write it down like that. So you know this can be written as 1 square root of 3 over 2 e to the I pi over 6. Furthermore, we write it down like that. We can factor out e to the I over 6. Why we do this? Why we do this? Factor this out. Does it matter?
No.
No, that's a global phase. It does not matter. So we're left with this. So this is equivalent. All right. So this 3 bars means equivalent. This is equivalent to this state, and this one looks similar to the parameterized version of the arbitrary qubit that showed to you in the prior slide. But it's not quite similar. Why it's not quite similar? Because I have a minus sign here. Let's do it further. Let's reduce that further. So minus sign can be written as e to the I Euler equation, Euler formula, and factor I into minus pi over 6, and we got this. Now, this is exactly what we have. Sorry. This is exactly what we have on the prior slide, which is cosine half theta plus e to the I phi sine half theta. So now we know with cosine, we know sine, we know phi. So now the theta is 3 pi and phi is 5 pi over 6. And on the blocks here, that's the point. Theta phi, and that's the point. Okay? So this point is on the block here. Is the qubit. That's where the qubit is on the block here. All right, so let me see what okay, in spherical coordinates, that's basically what I copied from the prior slides. Okay. So any questions about this block sphere mapping? Because the parameter version, so this one. This is a new looking. This is arbitrary qubit on the block sphere, and it has plus here. If you parameterize alpha and beta in terms of theta and phi, you have to put plus here. Otherwise, you won't find the correct theta and phi on the block sphere. Remember, phase here is really important. A minus sign will mess up completely. Will mess up your qubit completely, because -1 here corresponds to minus pi difference. Yeah. Okay. Cartesian coordinates, you know that, so I will skip that. So you know that, you know how to convert spherical coordinates to Cartesian coordinates, right? So I will skip that. Cartesian coordinates. This is how we convert spherical coordinates to Cartesian coordinates, okay? And you can find that on qubits. All right. So after this physical qubits, we're done with the single qubit session. Okay, remember we have 4 sessions. So we have 1 hour. We already have 1 hour. We'll spend 1 hour on this single qubits. And now, this is could be the most fun part of all my sessions. I'm going to show some pictures about physical qubits. Because this is more of, this is basically the state of the art qubit, I would say, production. How people actually create qubits in different platforms. Okay, so we write down the qubit in block sphere, and that's really abstract. Okay, and the 0, 1 is really abstract. But in the real world, how we create qubit. Okay, find how we define the 0 and 1 state. Okay, how we use the different bases and define that in a real system. Okay, so that's a physical qubit. So in quantum, any quantum system with 2 distinct states can be used as qubit. Okay, you can use on and off of the switch as a 0 and 1. You can use peaks and you can use peak or valley as a 0 and 1. So any distinct 2 states can be used as a qubit. Okay, so the first law, let's introduce photons. Okay, so with that in mind, any distinct quantum system with 2 distinct states can be used as a qubit. And now, what if the photon has 2 distinct states? A photon has 2 distinct states, and we can use photon as my qubit, right? And this 2 distinct states is photon's polarization. Do you know what is polarization? Do you know that? What is photon polarization? How many of them are actually physics majors? I would say. Well, let's just now use physics majors. I know it's gonna be really few people who are physics majors. How many of them have ever taken physics, college physics course? Okay, quite a few. And you should know the polarization of the photon, right? The polarization of the photon is the oscillation, electric field oscillation direction of the photon. And the photon is electromagnetism, it's an electromagnetic field. Right? It's a wave. So that's called particle wave duality. So it's a photon, it's a particle, but it's also a wave, it's like the electromagnetic wave. So this wave has oscillation direction, and that's the polarization. So if one photon has distinct two states, the two distinct polarization direction, you can use that as a qubit. Okay? So, and this is a photonic quantum computer. And this is reference. Not quite recent, it's 2018. So you know that electrons, if you build a circuits, the information carrier is electrons, right? Electrons flowing through the circuits, right? Flowing through wires in the circuit. Now, if we use the photons, and photons can be used as the quantum information carrier because it fulfills the statement here. Any quantum states that has two distinct states can be used as a qubit. So we use the photon as my quantum information carrier, and I build a circuit upon this photon. I can use that quantum processor, right? The wires in the electronics, like the wires in your cell phone, in the projector, in the computer, those wires guide the flowing direction of electrons, right? So if I make a chip that can guide the photon flowing direction, that's the photonic circuits. Okay? So that's the photonic circuits. So this is a quote-unquote photonic quantum information processor. Okay? So, yeah. I will talk about process fidelity. Okay, I will talk about fidelity when we talk about quantum error correction there. But this is one example. Okay, so let's go into another example. Shall we? Move on to another example. This is photon. Another one is whatever. What is that? Trapped ion. Do you know trapped ion? Have you heard about it? Trapped ions. So this is the ion state. And for honesty, like I just put a state here and I give you this quiz. Oh, any quantum system with two distinct states can be made as a qubit. What are the two distinct states here for the trapped ion? Huh? 0 and 1. Yeah? Energy state of ion can be used as a qubit. As these two distinct states. And this ion, trapped ion can be used as a qubit, right? Each ion can be used as a qubit. Photon has two distinct states on one photon. And if the ion has two states, 0 and 1, and then we can actually use it as a qubit, right? It's two distinct, right? Trapped ion. One of the IonQ, one of the most successful quantum computer company nowadays. The first public company, I think, in QIC machine. So they use trapped ions. Okay. So, all right. I should stand correct. What I just said is still right, but I use the visual aids wrong. That is why I see like 10 to the 14 to the 15. Why the ions so much? Actually. This is optical qubits. Okay. This is trapped ions. Okay. 0, 1 here. It still uses 0, 1, two distinct states. Frequencies are different. All right. Frequencies are different. Actually, it's a good thing. You know that optical qubit, the frequency is 10 to the 14th, 10 to the 15th, and trapped ion frequency is 10 to the 9th, 10th in the gigahertz range. And this is in the terahertz range. I see that, okay, that's terahertz range. Maybe I put it wrong visually, but it is correct. What I said is still correct, but it's just different, you know. This is the hyperplan splitting. That's the trapped ion hyperplan splitting, the trapped ion. You should find it out. You know this quite well. Yeah, so okay, so that's trapped ion. And do you expect more? Now we know the photon, we know the trapped ion. What else? IonQ, right now I brought a company called IonQ. What other companies, like, you know, subconsciously you should know, you should expect be a big player in this quantum computing computation? IBM? Yeah. Google? Amazon? Yeah. What are their qubit? Superconducting. Okay, that's superconducting qubit. So that's the circuit. Superconducting circuit. So superconductors is more of you know, two distinct. Still, you use two distinct states of the system. If so first of all, why the superconductor circuits? This is Google. Let me put up the visual aids, okay, so that you won't be bored by those texts. This is Google circuit, and this is IBM circuit, and this is Regni circuit. So those are the processors. This is really similar to what we have in this lab computer, laptops, right? Inside of it is called, this is called QPU, quantum processors unit. So that cluster there looks like more of a cluster computer. And they're, you know, those big companies have, they invested tons of money into this quantum computing computation. And this is what their circuit look like. And all of them actually will have, you know, that it's superconducting. The reason for it is, you know, first of all, you need to get to the superconducting circuit, the temperature, right? You need to cool the circuit down. So really, this circuit, this is not a whole computer, okay? The whole computer is really basically just here in the circle. Okay? And the rest of it is just to cool the circuit down. Okay? And so yeah, so the chip is really like this big, like no bigger than my palm. But the whole system actually occupies the room, the whole room. You remember that, you know, when Google announced that they are 52 qubits, it's 200 and 400. Recently, and you see a man standing, scientist standing on, you know, besides this giant chamber. That's not a whole computer, okay? That's the cooling chamber, okay? Well stacked. The only circuit actually is down there. And it's labeled as 20 millikelvin. You have to cool the temperature down to there. And the distinct states here are the equally spaced harmonic oscillator states. Okay? Harmonic oscillator potential. So as long as a quantum system has two distinct states, and you can use that as a qubit. Okay? Doesn't need to be only two. You can have multiple, but you just pick two of them as your qubit, as your distinct states, as your basis. And this is another one called neutral atoms. So we're gonna have a director in UTC Quantum Center. He's onboarding with us, and he's working on this. Use coded neutral atoms as the quantum processor. Okay. IBM is working on superconducting circuit, and IonQ is working on apparently trapped ions, and we're gonna have a new director here for our quantum center, and he works on this neutral atoms. Okay. Again, you can use the two distinct states. Okay. Two distinct states, and here is, you know, you can use this one and that one, 30 and 40 as the basis. Okay, as a computational basis. And nuclear magnetic resonance NMR, you can also create, you know, the qubit, cubic system based on this NMR. and I will not get into detail on that. Quantum dots, defect qubits. The point is, we can create the qubits out of so many different systems, right? We can create qubits out of different platforms, and different platforms have their pros and cons. Okay. That's the current stage. We're actually just basically exploring the pros and cons of different platforms. IonQ is a front runner. IBM, Google, Amazon, Regularly, they're all front runners on the qubit circuits. IonQ is on trapped ions. We hired a quantum center director working on neutral atoms. You see, there are different platforms. Okay, that's a take-home message. All right. So this is the current stage where actually right here, near-term application that you want a quantum computer, really you want to appreciate the quantum advantage of a quantum computer, you have to create the number of qubits in this machine. 10 to the 6. Right now we are here. 10 to the 2 to 10 to the 3. This is, you can have a fault tolerance scaled universal quantum computer. Scaled universal quantum computer. You have to create qubits in this number, all right? Sync is, okay, so yes. The number of qubits is what? No, that's the number of qubits. Meaning the number of what you just saw. Doesn't matter it's quantum. Doesn't matter it's photon. Doesn't matter it's neutral atoms. Doesn't matter it's quantum dots. Doesn't matter it's the trapped ions. You have to create those number of trapped ions. You get photons. You have to create this many qubits. Each qubit will have 2 distinct states. Yes.
We are not talking about the dimension. Two-dimensional.
The dimension is still 2. It works in a Hilbert space dimension, 2-dimensional Hilbert space. It's a pure number of qubits that you want to build upon. Like you want to create this number of qubits. You want to entangle superposition of. You want to maintain the superposition of them. You want to entangle of them for different algorithms, and you change the topology of different qubits. Those operations, you have to create at first hand those many qubits. And to have, I will talk about quantum error correction, and you will know why this fault tolerance is so important, because you create this million of qubits, most of them, 90% of them are actually used for correcting errors. Okay, so that you can have the quantum advantage for the quantum computer, from the quantum computer. The algorithm itself, actually, you don't need to assign this million, doesn't require a million qubits for some algorithms. You know, you can even use 5 Reinhold atoms. I just, the candidate talk of a quantum, soon to be quantum center director. His research just used the entangled 5 Reinhold atoms, neutral atoms, and could actually exhibit this quantum advantage. 5 of them, only 5. But if you want to implement this in the real life, you probably need to prepare 5,000 qubits. Only 5 of them is for the computation. 4,099 of them are for error correction. Yes.
Sorry, I kind of ask question maybe is still good.
Those 2 questions here.
You consider the number of qubits here, and if you is anything equivalent to see the current like 0, 1, the boundary in technology. How we is there any comparison here?
0 and 1.
Yeah.
Yeah, well, let's use the photonic qubits example, right? If you prepare a photon and it has 2 distinct polarization states, it's vertically polarized and horizontally polarized, and you assign vertical polarized as 0, you assign vertical polarized as 1. So you do the measurements. If the photon collapses to the vertical polarized state, that's the measurement result of 0. And the photon collapses to horizontal polarized state, that's the measurement of 1.
So there's always can be policy of the board is for sure it's the state with collapse.
Right, you need to assign a computational basis. Like for photon is each horizontal polarized V, vertical polarized. For trapped ions, then the hyperfine splitting of this of the trapped atoms there. You need to use that as the upper level of hyperfine transition as your 0 state, and the lower level hyperfine transition as your 1 state, or the other way around. Yeah, that doesn't matter. But you have to assign these two states as your computational basis. So if you find ions in that state, that's the measurement of 0. And you measure the ion, and it turns out the ion in the lower state, that's measurement of 1.
It's not quantum advantage. That's not an advantage, like that's classical.
So that's what I think he's asking that
That also my question. I tried to
You will see the quantum advantage when we go to when we
reduction.
when I talk about the quantum algorithms, and you will see the quantum advantage there. It's not about the measurement, it's actually about how actually you entangle those in input states. You always put 0 at the input, but you apply quantum gates, and then you create a superposition.
Yeah.
Hadamard dates like across the board, and then you see that they're all in an equivalent superposition.
I'm trying to look at the link using some.
Yeah. Okay.
Defining the space.
Quantum gates, yes.
Even photons we are traveling with it.
It's like I said, it's right. In real life, you basically have to assign the measurement results as your base. Like you have photon, and then the measurement base. I don't want don't want to get into too much detail about the technical detail. Basically, if the detector tells you, that photon is vertically polarized, you know that's 0. And if you tell the detector, you basically program the detector saying that when you get a photon which is horizontally polarized, report 0. And when you get a photon which is vertically polarized, report 1. But trapped ion, when the trapped ion is in the upper hyperfine transition, report 0. When the ion is in the lower hyperfine transition, report 1.
Is the limit to the number of qubits created like more physical limits, like space?
No, this is this is actually according to the algorithm, like algorithm developer, according to theoreticians. Experimental physicists are here. Tensor 2, Tensor 3, entangle the qubits. But for the algorithms to actually really implement, and that you can use the quantum computer to be the classical computer for any type of algorithm, you have to be here in this region.
So this number of qubits basically we try to find that it is driven by the algorithm.
This is driven by algorithm, yes. Yeah, so theory is actually we advanced than experiment at the like a real number of qubits that people can really entangle now here, can create our sheets in our entangle sheet to create essentially is 100 to 1,000. And algorithms people, we will have to, there's two theoretical fronts. One is you have to basically limit yourself into this many qubits. 1,000, 100 to 1,000, not even 1,000, like a few hundreds. And you have to develop some algorithms that you use this limited amount of qubits to see the quantum advantage, which means classical computer will not be able to do, or classical computer may have the disadvantage of processing this, the specific problem. And another another theory is the theoretical front of quantum computing research is can we actually come up with some solution, universal solution? Use as fewer as qubits possible. And what is the upper limit of that number of qubits? If you can reduce, you can come up with a universal solution like bounding error polynomial. I actually skip that part, like the complexity of those problems. If you have a universal solution for some specific group of problems, and only use the 10 to the 3 qubits, and that will be a breakthrough, right? That means the current technology can handle that type of problem universally. Okay. All right. Okay, so quantum gates. 4 minutes. We should stop here.
Yeah.
Yeah, 2:30. Should we stop here?
There was a question online.
In the chat.
There are 11 questions. Oh, no, this is actually just chat. If you measure, the question is, if you measure, observe it continuously, does it keep oscillating between 0 and 1, or does it change at the initial time of measurement and it stays there? It won't oscillate. It's just the one definite answer. It won't oscillate. Okay, so 0 and 1 at the superposition you measure it, it's either 0 or either 1. You don't oscillate. You don't oscillate like that. You just have one definite answer. I hope I answered that question. And it will stay there, of course. It will stay 0 forever. You collapse the state, if you measure it at 0, it will stay 0 forever. But now the question is, I skipped that section. If you measure it, turns out it's 0. And now I change the measurement state. If I measure it in the basis of plus and 1, plus and minus basis, what's the probability? What's going to be the measurement result? 50-50. It's again in the superposition. Because 0 can be written as 1 over square root of 2 of plus, minus. Now it's in 0, definite answer in 0 on computational basis. Now measure in plus basis or x basis. You got 50% of plus, 50% of minus. Okay, that's called consecutive measurement. You don't end up there. You don't see like this definite just there will be no superposition. No, there'll still be in the superposition. Depends on what is your measurement basis. Okay. All right, let's stop here and you have a question that wow. That's the
Which one? That's a question for, I think, the other costs.
yeah, those are the okay. All right, let's continue after the break. Okay, multiple qubits.
It's applied based on the calculation. Like signals on off 1 0.
One word, yes.
Stage.
On off.
Stage.
Yeah. One word to describe that is operation. Right? It operates on input state and give you the output state. Agree? So you change 0 to 1, or you change 1 0 to 0 0, 1 0, whatever binary state at the input, you get a new output, and then in this intermediate stage, we call that logic operation. And that's a gate. Okay, vector-wise, if you have a vector in 3 dimensions, x, y, z coordinates, Cartesian coordinates have vector, and you want to move the vector in the 3 dimensions, what do you do? You have a vector here, and you want to change the vector to a new vector, what do you do? Rotation. You maintain its amplitude, you maintain the length of the vector. And you times a what? You have a vector here. You have a new vector at the output. What do? In linear algebra, you times a matrix. You times a vector with a matrix. You convert this new vector to you convert this old vector to a new vector. Okay. Same thing. So in linear algebra, quantum gates is a matrix. Okay? It's a matrix. It's an operation. It's a manipulation. Okay? It changes, it relates input to the output. Okay? Just like a classical game. And it's frozen again. Linear. Okay, good. So if you have we will use here, if you have the input state, like you have the input state 0. Suppose you have input state 0, okay? And you want to have the output state like this, which is superposition of 0 and 1. And you use U to transform this 0 into that superposition. And this U here is a quantum gate. It's a gate. Let's first now use quantum, because quantum actually specifically for something. It's more than just a transformation, or more than an operation, or more than a matrix. But now you should understand that when I have input state 0, which is a vector, and I want to just change the vector to another vector or rotate the vector, I like the rotation. I like the term rotate because it maintains its amplitude. Right? We rotate a vector in 3 space in 2 dimension. We multiply a matrix U to get a new vector. Okay? So that we use U to denote the quantum gates, and you will know why we pick letter U to denote quantum state. It has a specific meaning. It alerts you U means unitary, and we'll get to that later, very soon. So you apply U on 0, you transform 0 into a superposition of 0, 1. You apply U on 1, you transform the 1 into superposition of that. So that's a operation, that's a transformation, and mathematically speaking, that's a matrix. Okay? So quantum gate must be linear. Why it's not linear? Why quantum gate must be linear? Because quantum operation is based on linear algebra. So it must be linear. Right? So what is the classical computation based upon? What's the algebra classical computer based upon? Computer scientists? Boolean algebra. Right? Quantum computer is based upon linear algebra. So that's why it must be linear. What does the linear mean? That U applies onto an arbitrary qubit, alpha and beta. Remember this arbitrary qubit notation? And U has to be uniformly applies onto 0 or 1. Okay? Linear algebra. Linear. Must be linear. So U on 0 transform to that, U on beta transform to that, and then you will have this new state. So you apply U on an arbitrary state, and then you got that. Okay? Arbitrary unit, you got that. It's linear algebra. And it's a quantum gate. It's a transformation, it's a linear, it's a matrix. Okay? So for the quantum to be valid, this transformation should maintain the probability to be 1. Okay? So this transformation more of just a rotation. Okay, it rotates this, the point on the block sphere, it just rotate the point from one point to the other along the block sphere. Okay? It has to maintain the probability to be 1. Okay? All right, I think this is pretty intuitive, right? Yeah. All right. So to prove that, this is just a proof. Okay, so for the unitary transformation, you maintain probability to be 1, and you add this, you do the unitary transformation, you got 0 and 1, now you have this new probability amplitude for 0 and a new probability amplitude for 1, and you add them quadratically, you calculate the square, modular square of these two, you add them together, and that's 1. And now U is a valid quantum gate. Okay? You can define the quantum gate at your own leisure. That's your degree of freedom. This is a great example of a quantum gate you define. You define a quantum gate, you start from scratch. You work, first of all, you pick. I want to work in the computation basis, 0 and 1. Done. Now, I want an operation that transform 0 according to this, transform 1 according to this. Okay, that's an operation. That's the quantum gate you created. Thus, U is a valid quantum gate. You need to do the sanity check by adding these two new modulus, probability amplitudes squared quadratically. Turns out they're 1, it's a valid quantum gate. Okay? Now I just explained a quantum gate in terms of linear algebra. All right? There's no physics involved in it. It's basically just a matrix. Agree? It's just operation. And this operation maintains amplitudes, probability amplitudes, total probability amplitude. So we want. So quantum gates are linear maps that keep the total probability of states equal to 1. Unitary. U. Any questions? No? We're gonna have some examples, all right? For the common quantum gates for 1 qubit. Okay, there are some common examples. Yeah, so this is a slide still. Dr. Cox and Dr. Lan, we co-teach this course. So, okay, so that's why you see the statement there. I introduced this quantum gate concept in terms of operation, and in linear algebra, it's just a matrix, okay? Quantum gates. I will skip this classical reversible gates. Do you know the reversible? What does reversible means? Do you know that? First of all, if you see this Boolean algebra here, if you see this, what is this, first of all? If you write A, B, and 0, 1, 1, 0, what does this? What does this mean? There's a name for this notation. What? This is a table, right?
In math, we call it a truth table.
Truth table. This is a truth table. If a gate, so A means input, B means output, right? So if your input is 0, your output is 1. If your input is 1, your output is 0. What is this gate? Not gate. Not gate, right? Okay. If I give you the outputs, I give you the output of 1. Do you know the input? 0. If I give you output of 1, 0, do you know the input? 1. So that means it's reversible. If I give you the output, you can trace back to its input. There's no ambiguity there. If there's a gate that I give you the output 0, and it could be 0, could be 1, that means non-reversible, meaning you lose information. It's the output 0, and I have the output 0, and then I do not know the input. It could be 0, could be 1. that gate is non-reversible. Okay, reversible means this. So quantum gate has to be reversible. All right. So I will skip that. Classical reversible gates are valid quantum gates. Okay. Classical reversible gate is a valid quantum gate. So you can basically, if you don't have a recipe to create a quantum gate, if you don't have a recipe to create a quantum gate, you can use classical gate. But this classical gate has to be reversible, like a NOT gate. Okay? You can use a NOT gate to create a quantum gate because it's reversible. Not any classical gate has a quantum gate counterpart. That classical gate has to be reversible, and then you can have a quantum gate counterpart of that. Equivalently speaking, classical reversible gates are quantum gates, are valid quantum gates. Any classical reversible gate. Okay? All right, so irreversible gates are now quantum gates. All right, so how to make the reversible gate, any classical gate reversible? It's not our interest, right? At least for this workshop, we're not interested in making the reversible classical gate. Non-reversible classical gate reversible to make a quantum gate. It's not our interest. It's a recipe. There's a well-defined recipe there. So I will skip that. Okay? I will skip this. But you need to remember, there are two types of classical gate. One is reversible, one is non-reversible. Any reversible classical gate is a valid quantum gate. Non-reversible classical gates, you need to apply the recipe to make it reversible so that it can be a quantum gate. Okay? All right? All in all, the gate has to be reversible. All right, so common single, let's get into this. Common single qubit quantum gate. Okay? Identity gate, the first one. Identity gates, you apply there. Now I will write down why I will not use truth table. I will use linear algebra across, along the rest of the slides. Like this. 0, you have inputs, you have outputs. I matrix, identity matrix. You apply I to input, you got output 0. You apply the input I, you put 1, you apply I, you got 1. The identity. This is a classical reversible gate, identity gate, right? It's a valid quantum gate. The second one is I put here is poly-X gate or NOT gate. Turns 0 into 1, turns 1 into 0. It's a NOT gate. For computer scientists, you like NOT. For quantum physicists, for quantum people, actually not quantum, for quantum people, they use poly-X gate, okay? All right, it's poly-X gate is a NOT gate. It turns 0 to 1, it turns 0 to 1 to 0. So X poly-X gate, apply on 0, turns 0 to 1, and turns 1 to 0. Are you able to write down the X in the matrix formation? Let's leave that to Chris. Chris, have done your session. All right. I assume you're gonna you know how to do this, okay? And you know that X is a matrix, okay? And this actually is called poly-X gate. In quantum physics, it's called poly-X matrix, okay? So it's a NOT gate, and in the block sphere, this gate, like I said, gate / operation / transformation / matrix. They're equivalent. So in the block sphere picture, this X gate just rotates the qubit or the vector on the qubit along the x-axis by 180 degree. So that's why it's called poly-X matrix. Okay, so this is operation. This is a graphical representation of poly-X gate. The operation that poly-X gate does to the qubit. Okay. So, is it this poly-X matrix, you rotate the poly-X matrix by 100 degree. If you rotate another 100 degree, it rotates back to the original state. So that means x squared is equal to I. Right? So the poly-X matrix square is equal to the identity matrix I. Because intuitively, right, you rotate 100 degree, you rotate twice, you return it back, So this is a poly-X matrix, and naturally you would expect if you have poly-X and you can rotate on the x-axis, what are other rotations you can do? Y and Z. So they're called poly-Y and poly-Z. So next one is poly-X, this one is poly-X, next one is poly-Y, turns 0 into the I1, and it turns 1 into minus I0. So that's poly-Y matrix. And this is along the y-axis rotate by 100 degree. On the y-axis and rotate by 100 degree. Okay? And you rotate twice, you rotate 360, you got back to original state. I will speed up, okay? This is pretty intuitive. Okay, and poly-Z turns 0 into the minus, turns 0 into 1, on the z-axis, turn 0, doesn't do anything on 0, but turns 1 to minus 1. Okay, so that's along the z-axis. So that's along the z-axis. And you turn twice, you got I back. You got the identity matrix. All right. Base gate. We have identity gates. We have poly-X gate, we have poly-Y gate, poly-Z gate. Now this fourth gate. This is the fifth gate, which is the phase gate. Phase gate is basically the square root of Z gate. So that means the Zx squared is equal to Z. If Z is rotating by 90 degree, what do you expect S gate would do? Z is 90 degree. How does S gate do to the qubit? 45, right? It's 90. Z rotates 100 degree, 180. So Z squared, S squared is Z rotates 180. Square of that is double the phase. 100 degree divided by 2 is 90. Okay, so it rotates along the z-axis, it's still related to z-axis, but it's no longer rotated by 90. Now, it's no longer rotated by 180, now it's 90. So that's Z. And now you need to, if you want to get back to the I identity, you need to rotate 4 times. 4 quadrants. 1, 2, 3, 4, and get back to I. So the S4 is equal to S squared 4 is equal to I. Okay? Phase gate. And then the last gate is the T gate. Now it's quarter pi gate. You see that it's not 90, now it's 45. Okay, so it's T squared to the S gate, phase gate. So you give the 1 and a quarter base, pi over 4 base, 45 degree. Now 90, now 180, now it's 45. Okay, so it's rotate by 45. And you have to rotate how many times? 8 times to get back to the identity. Now those are the common gates, okay? Identity, poly X, Y, Z. And Z, the derivative of Z gates is S gate, which is the phase gate, and then this T gate. They're all different by rotation angle. Z rotates 100 degree, phase gate rotate by 90, S gate rotate by 45. Okay? Those are gate. And remember, gate are the operations. Gates are the operations, are the linear transformations, and are the matrices. Okay? And the last one probably is the most important one, is the Hadamard gate. Okay, I see it's the most important one because this guy does not have any classical counterpart. Why? The Hadamard gate turns 0 into plus, turns 1 into minus. It's a superposition creation gate. It creates superposition. So that means if you apply Hadamard gate to 0, you got a superposition of 0, 1. If you apply Hadamard gate to 1, you again got 0 and 1 superposition. Right? So you apply Hadamard gate to the computational basis 0 and 1, you got superposition. You turn 0 to plus, you turn 1 to minus. This is a Hadamard gate. For quantum circuits, for the session, for the tomorrow session, and you will know that to observe the quantum advantage for the quantum algorithms, Deutsch-Rosa, Gruber's algorithm, Shor's algorithm, whatever algorithm that, the very first step is to apply Hadamard gate to create superposition. Okay? So that's very important. Okay, remember Hadamard gate is a superposition creator. Okay. On the block sphere, it rotates, still rotates on the block sphere, but now the axis is no longer its traditional x, y, z. It's a new axis, rotational axis, which is x plus z, which is 45 axis on the xz plane, and rotate this along this axis by 90 degree, or 180 degree. And that's the representation or the operation of the Hadamard gate, okay? It's a new rotational axis, which is x plus z, okay? So H maps between 0 and 1, between 0 and plus and 1 and minus, okay? And between I and minus I. So this statement implies that if you apply H gate on 0, you get what? You get a superposition of 0 and 1, you get x. And if you apply H on 1, you got minus, and vice versa. You apply H gate on x, you got 0. You apply H gate on plus, you got 1. You annihilate their superposition. Why is that? You just learned the term. You can do that. The H gate can do that because it's reversible. Okay? Because it's reversible. Great. Okay, so and again, H square is equal to I because you apply twice. It's 360 degree. I think that's it. Quantum gates. Now those are the common quantum gates. Okay, let's review. Identity gate, only X, Y, Z gate, phase gate, S gate. Z as phase gate, which is denoted by S gate, and then there's the T gate, right? T gate 45. They're all related to the z-axis, but just rotation differently, right? Rotate by 180, 90, and 45. And then there's Hadamard gate. Those are common single bit gates, okay? Single qubit gate. They work on the single qubits. Okay? They work on the single qubits. So that's called single qubit gate, quantum gates. And you will learn multiple qubits gates. Multi-qubits quantum gates, okay? They work on multiple qubits, okay, at the input, all right? So general 1 qubit qubits, 1 qubit quantum gates is basically just a rotation on the block sphere, This concept, you know that. I brought this concept at the very beginning of this session, right? Gates, one single qubit gate is a rotation on the Bloch sphere. You see that? You appreciate it. You have already seen that. Apply those gates, just rotate the qubits along the Bloch sphere, right? On the Bloch sphere, right? So this single qubit gate is just a rotation on the Bloch sphere. It's maintaining its rotation. But what if the qubit is a generic qubit? Right? What if the qubit is a generic? And on the 3-dimension, Bloch sphere is 3-dimension, and the axis, the rotation axis is generic. What if the rotation axis is generic? And n is my rotational axis. Now, if you are still with me, I hope you're still with me, that rotation is the axis on the Bloch sphere. And if I pick this quantum gate, an arbitrary quantum gate, which is arbitrary rotation on the Bloch sphere, and that rotation axis is written in terms of n, what is n hat there? N hat is what? It's a vector, which is along the Bloch sphere. And this vector is a unit vector because Bloch sphere is a unit sphere. You write down the vector in x and y and z, and in maintaining the norm, they have to be add up to be 1, the square. So if the rotation is arbitrary, can we write down the quantum gate? Can we write down the quantum gate? Meaning, can we write a universal matrix that rotate a vector on the Bloch sphere? Can we write down that? Basically, the question boils down to, can we write down n in terms of spherical coordinates? Okay, so I don't think I need to spend too much time there, and that's how you can do that. So basically, you write down these in terms of spherical coordinates. You will have the theta and I. Well, you have the you have the gamma, which is global phase, and you have the theta, which is the phase on the Bloch sphere, and this is the arbitrary rotation one qubit matrix, or 1 qubit gate. Okay, you write it down. See, look at it. Look at it. So you will have you could simply drop this gamma term because that's a global phase, right? And what you are left with? Tell me. You have this spherical coordinates information, which is theta there. And what else? What else you are left with? What are the other components in this equation, in this identity? X, Y, Z, and what? And I, identity matrix, right? I is identity matrix, X, Y, Z are the poly X, Y, Z matrix. So if you want to rotate this, want to do an operation on a single qubit, you just want to pick up along an arbitrary axis by an arbitrary rotation, meaning theta. You just write down this equation. You write down theta. I want to rotate my qubits by 23 degrees along nx and y and z arbitrary. And this quantum gate can be written in this way. You plug in nx and y and z, you plug in the angle you want to rotate, you desire to rotate, your quantum gate is going to be like this. Okay? Because you know identity matrix I, you know poly x, y, z matrix, and you know your axis, rotation axis, and theta. You can write it down like that. Okay? This again, just to prove that for a single qubit, the quantum gate on a single qubit is just a rotation on a Bloch sphere. For example, if you want to rotate a theta along this axis, which is 1 over square root of 2, 1, 0, 1 over square root of 2, with the theta equal to pi, if I just put this statement here, what is this? I want to rotate n hat, which is written at Cartesian coordinates as 1 over square root 2, 0, 1 over square root 2 with angle of pi. What is this operation? You learned this. What is this operation? It has a name. Yes, thank you. This is the Hadamard gate. It rotates along the x plus z axis, which is denoted by this n hat. This is the x plus z axis, okay? By pi degree, 180 degree. So this is Hadamard gate. Let's prove, is it Hadamard gate? It is. If it is, it should, if this actually will, so just basically just prove that if this turns out to be a Hadamard gate, if we just do the plugging all the poly x, y, z and identity matrix, let's do that. So we plug, this theta is pi, we plug in theta pi here, and then you plug in n x and y and z, which is 1 over square root 2, 0, 1 over square root 2 there, and then you end up with this. And that's the Hadamard gate. Okay? You drop this global phase, right? You can drop it, right? That's global phase. Any questions? I see a lot of confused faces there. You end up with this gate, x and y, and the Hadamard gate turns 0 to 1. Sorry, Hadamard turns 0 to plus, turns 1 to minus. No, turns I to minus I, right? So this is the gate written in terms of poly x and z gates. So if you apply this to 0, you apply that to 0, you apply poly x, poly z, and you turn to x. You drop the global phase, you turn that into plus. Right? And then you apply this gate. Again, on the 1, you expect that you will turn 1 into minus. That's the universal 1 cubic gate. Example to show that everything can be reached in terms of that. As long as you know your rotational axis, the coordinates for the rotational axis, as long as you know your theta, you can write down your single beat quantum gates in terms of that. It's just I, x, y, z, the combination of I, x, y, z. Okay? All right, let's get into the multi-qubits. Let's study entanglement. How about that? Refused, reluctant. All right. Okay, so those are the subsections or the topics will be covered in this section. The quantum multiple qubits. Again, measurements. I know you hate this term, measurement. Okay, but we need to study that. Okay, it's the most distinct property between quantum and classical. Okay, it exempts the quantum exempt itself in the measurement. Okay, if you don't do measurement, you don't know it's quantum. Okay, so it's measurements and then entanglement and then multi-qubit quantum gates and then quantum opening theory, and I will escape quantum error correction for the interest of time. Okay, I don't think I have enough time to get into that. Although it's just a few slides, but it's pretty involved. Do you know classical error correction? Do you know classical error correction? Do you know the, yes. Do you know the parity method? Yes. Only you? I think that's also yes. Okay, so that means I have to introduce parity method classically, and then you will know quantum error correction. Anyway, it's too much involved. So we will cover the first 4, okay? Measurement, entanglement, quantum gates, and quantum opening theory. Okay? All based upon single qubits. All right, multiple qubits. So 2 qubit states. Again, I will start this section in terms of the 0 and this direct notation, 0 and 0. So what is this open circle with a cross? That's a tensor product, right? So now you not only have 1, 0, you have 2, 0, and you write down this two state, multiple qubits. Now, because you have multiple qubits, let's start with 2, right? There's 2 qubits and 0, 0. You write down and they're in tensor product, 0, 0, and we can further reduce to this. And this bracket and bracket. No, sorry, I should not say bracket. It's vertical and right pointing arrow and vertical right pointing arrow, and you can even reduce it more to this. So I will bring this up is for you. I mean, it's simple, right? It's so straightforward, but I want to actually to stress that when you see this 0, 0, you should reflect to here, to the tensor product. Okay? When you see 0, 0, you should reflect to the tensor product. Now I ask you, if you do this, answer my question. What is the dimension of 0, 0? If 0 is 2 dimension, it's 4. Do you all agree? Dimension is completely different. It's double. It's 4 dimensions because that's tensor product of the two-dimensional vector. That's a tensor product. Okay? All right. Now, if for single qubit quantum gates is a matrix, how about for multiple qubits? The quantum gate is 1. It will be. Is that a matrix or is that a? It looks like a matrix. It's a tensor. It's a tensor. So this is actually off topic. What is a tensor? What does tensor do? If you have the one vector here, this is the input. And you multiply this input with a matrix, you convert this to a vector. That's the output. Agree? One vector, one matrix, one output. This is a matrix. When it will become a tensor, it looks like a matrix. Agree? When it will become a tensor.
Each element is a matrix.
It will become a tensor when this input is not only one vector. It will have multiple vectors there. If this output vector is determined by multiple inputs, this is a tensor. Just like this. The output is determined by 2 vectors here. So that's a tensor. Don't see a matrix, okay? It looks like a matrix. All right, so I want to just give you that with 2 qubits, there will be 0, 0, 0, 1, 1, 0, 1, 1. Right? This is our new Z basis. If I have 2 coins, what do you got? The combination of the heads, tails, tails, and tail. Right? So for 2 qubits, it will be 4. It's 4-dimensional. It's not 2-dimensional. It's 4-dimensional. Meaning you are gonna have 4 orthonormal states, 4 eigenbases, 4 eigenstates. So 4, and they are 0, 0, 0, 1, 1, 0, 1, 1. And a general superposition of this is that.
I have a question.
Yes.
So regarding the interpretation between matrix and tensor, so can we assume tensor is like matrices stacked on top of each other? Can we?
Yes. Perfect. Yeah, intuitionally, yes. You basically have this one's here, this one's here, this one's here. That's 3 dimension, right? 2 dimension. Here, 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 here. That's 2 dimension. But each one will have 2 by 2, 2 by 2, 2 by 2, 2 by 2, and that will be 16, right? And then you have 3 dimension. That would be 9 times 27. That's right. You step each other on top of each other, right? So the matrix is this quote-unquote tensor is basically contains multiple matrix there inside of it, and collectively it looks like a matrix. But it's actually, if you dissect those different parts, this corner corresponds to this one, right? If I don't want. And this corner corresponds to that one. I think that's, there's a trick there. I don't quote on me, but you're right. You're right. It's tensor on top of is matrix on top of each other. Yeah.
That's what each element.
Each element, yes. Each element is matrix. Yes. All right. Okay. So now the superposition is no longer just 0, 1. Now it's this for this 2 qubits basis, 4 dimension, the superposition will be this. And how about 3? If I have 3, 8, why you got 8? 2 to the 3's power, right? So you have n qubits, you will have 2 to the nth power. All agree? Okay, so, but no matter how many coefficients, so each one of them will have amplitude coefficients, and then those should add up to be 1. Okay, now you have 4 probability. Now if you do the measurements, you're gonna get 4 different results. But they're just basics, right? They're just eigenvectors. You're gonna collapse the state into the eigenvectors of that space. You have 4 distinct results. And the probability for each one of them add up to be 1. Generically, if you have n qubits, this is gonna be your generic state. That's 1 state. That 1 result that you could measure, right? And you write that down in terms of that. So that will be, why I could write down like that? If you let's just use an example of n equals to 2, or equals to 1. Let's just use, no. Let's use n equals to 2. If n equals to 2, what is that? So if n equals to 2, let's use b0 of 0. Let's name b is b, so n equals to 2, b0 is, for example, b0 is 1. Let's use a b0 0, b1 is 0. What does this correspond to? You know that n is equal to 2. N minus 1 is 1, so that's 2 here. So b0 is 0, b1 is 0. What does this correspond to? 0, right? And if b0 is 0, b1 is 1, what does this correspond to? 1. What is the highest number you can get on the right-hand side? What is the highest number you can get on the right-hand side here? What is the highest number you can get on the right-hand side? You make 0, b0 1, b1 1. What is this number? That's an integer. Plug in this number. This is 1. This is 1. 2 plus 1 is equal to 3. What do you get here? So you basically have 0, 0 is equal to 0. 0, 1 is equal to 1. 1, 0 is equal to 2. Yes, thank you. 1, 1 is equal to 3. 0, 1, 2, 3. That's n equals to 2. How about n equals, if n is a large integer, this guy will be, what do you expect? What if n equals to 3, what's this number?
Yes.
7. Okay, so that will be from 0 all the way to 7. Okay. All right. Okay, so, and this is gonna be also position state. Remember, this is true. Can you see this clearly back there? I don't think you can see it clearly. No, we cannot see it clearly, right? So this is 0, 1, 2, and 3. So if you write down, if you see the literature, this is why I brought this up. You see the literature, when n is a really large number, for example, 42 qubits, which is actually most of the company affords 42 qubits, around 40 qubits for you to do the quantum algorithm. So you can have 42 qubits. Now you can buy credits so that you can work on a real quantum computer. So if they give you 42 qubits, how many states do you expect? 2 to the 42 power minus 1, right? In binary format, each state will contain 42 binary bits. Agree? Start from 0 all the way across the board to 0. And end with 1 all the way across to 1. 42 of them. Superposition. To reduce the calculation or to use the notation, you use 0 to 2 to the 42 power minus 1. Okay? Did I say this clearly? Right? So for example 3, you don't need to write down 0, 0, 0 all the way to 1, 1, 1. You just write down 0, 1, 2, 3, 4, 5, 6, 7. And make them a superposition. Because 7 is equivalently to 1, 1, 1. All the mutations. So that's why you write down like here. So don't be confused. Some literature actually just actually throw this out without any explanation. What is this? What is 121? It corresponds to, you have to convert 121 to this binary string here. You know that's a binary string, right? What? Okay. So yeah, so just give you a flavor that if you have n equals to 3 qubits, and then we have to keep track of how many coefficients. 2 to the 2, 300 minus 1, and we just ignore 1. Okay, 2 to the 103. And that's 2 times 10 to the 90 amplitudes, which is more than the atoms in the universe. How many atoms in the visible universe? We don't count dark matters. 62 or 70. Depends on which model you use. Yeah. So it tends, so it tends to 78 to 10 to, this is a very conservative estimation. It could be overestimated. So it tends to 78 to 10 to 82. So if you have 300 qubits, if you entangle 300 qubits, you need to keep track of the amplitudes, the different results, right? More than the number of atoms in the universe. I don't think did I open this? Sorry, it was just a ton outline. All right. Now you know that. Technical glitch. Oh, we learned a lot. Okay. Yeah, so how many qubits we have entangled so far? Commercially, we're able to acquire 42 qubits commercially. And I think Google has a record, 242. Yes. Quantum supremacy paper. Yeah, 242, something like. But that, I think it's the Boson sampling. It's kind of pretty useless algorithm. So yeah, so we're actually close to this qubit. Okay, we're able to entangle this, and you would know how we actually get a superposition of this many qubits states. You will know that just by simply applying Hadamard gates. Okay, all right. So you write down the generic n qubits. This is about the notation and also about some misunderstanding. Yeah, so if you write down this in terms of that, you should know that there's some literature write down this n to the nth power. Some prefers this, just to emphasize its tensor nature. But you should know that this is a tensor, okay, with n dimension, okay, with two nth dimension. Was 2 to the nth dimension. Sorry, 2 to the nth dimension. So with a single qubit, we're not able to. So remember that when we want to parameterize the 2 qubit states, we could use a block sphere, right? Means we can parameterize the amplitudes alpha and beta in terms of theta and phi, and theta is the angle formed by the vector with the z-axis, and phi is the angle projected onto the x and y plane. So that's for single qubits, and for this n qubit state, we're not able to parameterize. So there's no visual aids for you to see the qubits in dimension, in multiple dimension. Okay, so parameterize is too much complicated. But at least we have block sphere to play around for single qubits, okay? Canonical product, this is all about tensor, and I will skip this. Okay, so this is this matrix on top of the matrix. So that's why you see that, okay, I want just to show that. So if you write down the vector information, the representation, I call the vector representation, it's not vector, it's a tensor, okay? So 0, 0 means 1, 0, 0, 0. And 1, 0, 0, 1 means 0, 1, 0, 0. And 1, 0 means 0, 0, 1, 0. And 1, 1 means 0, 0, 0, 1. Okay? It's obtained from the tensor product of these two. All right? Okay. So, and then I want to remember this. Also, this is important, but also, like, if you write down this generic qubit states in terms of C0 all the way to C3, those are the what? Tell me. C0 and C3 are the what? Yes, probability amplitudes. Okay, if you see a vector, 2 qubit states, 0. This is a generic qubit state, and represented by this, you should reflect to that this C0 all the way to C3 are the probability amplitudes. Okay, they're probability amplitudes, all right? And then generically to n qubits, and you can write it down like that. How nice it is. You don't need to write down this superposition from C0 all the way to n minus 1. Remember here, n is equal to 2 to the nth power minus 1. You don't need to write down like this. This is the superposition, but you just write down a C0, a vector, looking tensor product. From C0, from top to bottom, C minus 1. And remember, each number, it's complex number. Okay, I'll call it number. Each number represents the probability of finding its state. So C0 corresponding to the probability of finding this. Oh, sorry, I use this now. The probability of finding C0 of finding this, which is this state. And C3 is probability of finding obtaining the measurement result of 1, 1. Okay, and you write those probability amplitudes in this way. Okay. Now let's talk about measurement. How about that? We talk about measurement in the single qubit session. Now let's talk about measurement in the multi-qubit session. We know how to write down the superposition. Now let's talk about measurement. Because now we don't have one qubit, we not even have one qubit, we have multiple qubits, we have 2 qubits. Let's use 2 qubit as example. Okay? So if the qubit is written in this way, here, and you have 1 over square root 2 across, this different qubit there, right? Combination there, and what do you expect the measurement would be? It will be just 0, 0, 1, 0, 0, 1, 1, 1, right? With different probabilities. So those are the probabilities of getting 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, right? But if we just concentrate on single qubit, now here's the key difference. If we want to concentrate on this single qubit, only the left qubit, only the left qubit, only the left qubit, what measurement result you're going to get? If you only measure the left qubit, like this is your left qubit, 0, 0, 1, 1. What's the measurement result you're going to get? Left qubit. It's a single qubit. It's a left qubit. Single qubit. It could be just 0 or could be 1, right? You only get 2 results, 0 and 1. Now, the harder question: what is the probability of getting 0? Why it's 75%?
1 over 2 plus 1 over 4.
1 over half plus 1 over 4.
This one plus this one.
Yeah.
All agree? If you don't understand this, quantum computing is really I think you're gonna find yourself really hard time of understanding quantum computing. Multiple qubits. Okay, let's just rephrase the question again. If you only measure the left qubit, you got 0 result. You got 0. What's the probability of getting 0? Only left qubit. You can add these 2 probability amplitudes together. 1 over square root 2 plus 1 over 2. Right? Because if you get 0 on the left qubit, there are 2 possible states for you to get to have that left qubit to be 0, which are these 2. Right? So you need to add these 2 together from the amplitude. So if you get 0 with probability of 3 over 4, and the state collapses to this. Collapses to. You don't have the 4 combinations. Now you only have 2 because your left qubit has to be 0. And this renormalized to be 1, which I skipped it. I hope you're still able to calculate how to renormalize it. It's calculated from this 2 probability, but that's not important. The important thing is you need to understand that if you only measure the left qubit and then it turns out to be 0, the probability contains 2 parts because you have 2 states that corresponds to the left qubit to be 0. And that's how you do quantum error correction. You don't collapse the qubit you care about. You collapse the qubit. You don't measure the qubit you care about because this qubit contains the computation task. You only measure the qubits for the error correction. Okay? Again, if you measure 1, then the probability will be one quarter, right? It will be this and that. And the state collapses to that. Good? Work on that if time permits. This is the reminder. Work on the whiteboard. Yes. The 3 over 4 come from? The 3 over 4. This one. You add this to you add 1 over square root of 2 square plus 1 over 2 square. It's 1 over 2 plus 1 over 4. It's 3 over 4.
Yeah, about one, that's amplitude, so that 3 over 4 is the magnitude. Or the low more.
This one?
Yeah.
It's the probability.
Yeah, okay, back up.
Yeah, it's probability. It's not probability amplitude.
Understand.
Okay. Okay. All right. So let's skip that one because that's a generic case. That's for the 3 qubits. I will skip that entanglement because I have 5 minutes for entanglement. Okay. So entanglement. And what is entanglement? You heard this term many, many times, right? On the literature and article in news all day. What is entanglement? What is your understanding of entanglement?
Spooky action.
Spooky action at distance. Einstein's famous phrase, right, to describe entanglement. Why does spooky action will happen at a distance? Because you measure one, you know immediately the other, right? How do you know the other? Why you measure this one, you know the other? Because they are correlated. If they're not correlated, you don't measure. You measure one, you do not know the other. You don't care because there's no correlation, right? Like if you work on a homework and on an exam, and if your study time is not correlated with your score, you don't study at all, right? Because you work on the exam, and the more you work on the exam, you get a high score. You know. Here, so if you measure this, you know the result because they're correlated. And this correlation is spooky, means it cannot be described in a classical way. Here, the classical way means that measure the state here, the particle state here, you will know the particle state here. At the instant, you know the state here. Even one is on Mars, other one is on Earth. So you measure the one on Earth, and you know the result, and immediately you know the measurement, you know, the state on the other one. You collapse the state on the other one. You know that measurement on the Mars will be something. So there's no communication between Mars and Earth. It's faster than the speed of light. No. No, definitely no. But to see the collapse, the state collapse is faster than the speed of light.
Yeah. But the information doesn't cross.
Information is physical.
Yeah.
You cannot use this collapse of the state wave function to convey any physical message. Okay? So it's basically, the entanglement basically just a non-classical correlation. Okay? So that's a physical approach, like, you know, kind of like conceptual approach of understanding entanglement. So if we have a quantum state like this one, can we write down a quantum state like this? Can we write down a quantum state like this, for example? Nothing prevents us from writing down the quantum state like this. And what's the requirement of writing down a quantum state like this? What's the only requirement? The probability has to be 1. So the probability amplitude has to be added up to be 1. And does it fulfill that condition? 1/4, 1/4, 1/4, 1/4. It's 1. So that's a quantum state, right? Valid. So it's superposition of 0, 0, 0, 1, 1, 0, 1, 1. Right? So this quantum state can be written down in terms of the 2 product state. Meaning you can write down this quantum state in terms of the left-hand side, this one and that one. Tensor product, this one and that one. What is this? At the very beginning of my section, what is this? This is a plus. What is this? That's a minus. So you write down the quantum state in terms of plus and minus. So you write down the quantum state further. plus tensor product minus, plus minus, and then it's just these two quantum states, right? It's the product state. It's the product of the plus and minus. That's a quantum state, which contains two parts. And you can resolve these two parts, and you can put plus on the left hand side, minus on the right hand side, in tensor product, you get that quantum state. So that's factorizable, and it's called product state or the separable state. So what if we have this state, like here, this one? Oh, this is the, it's 4 o'clock already. So if we want to write down a state which cannot be factorized, meaning we have a superposition of 4 of this 0, 1, 2, 1, 1, but we're not able to find any basis to write this superposition into the basis, like into plus, minus, I, 0, or 1, 0, need a computation basis. We're not able to do that. For example, if this state, like, 5, 1 over square root of 2 plus 1 over square root of 2 is 0, 0 plus 1, 1. So this state contains only 2 results, 0, 0, and 1, 1, and there's no 0, 1, 1, 0, right? Can we factor this? Can we factor this? So let's do it. Okay, I will just use 2 minutes. I will just, occupy you 2 more minutes to see that this is not factorable. Let's assume it is factorable. Then you can factorize into 5 plus and 5 minus. Okay? So, oh, I need to work that. Oh, where's my slide? It's not there. All right, I'll catch this up tomorrow morning. Okay? Basically, spooky action at a distance is the conceptual understanding of entanglement. In the linear algebra, if a state cannot be factorized into 2 separable states, which is in the 2-dimensional Hilbert space, if you use 4-dimension 2 qubits, okay, and they're called entangled state. Literally now, from now on, you should just reflect entangled state as non-factorizable. Like the one you just saw, the state you can factorize in terms of plus and minus. There's no combination of single qubit state for you to factorize the state, and that state is an entangled state. Okay? All right, I'll see you guys tomorrow morning. For quantum protocols, for quantum teleportation, supernodes coding, QPD, and I will cover, I hope I will cover 1 algorithm, Deutsch-Hofer algorithm. Okay?
I've been working on that thing. I kind of started working on it again, the 3D